This is the index for the 12 modules present in Dampness in Buildings and Diagnosis. Welcome to Dampness in Buildings and Diagnosis, Module 1 of 12. We'll start off by having a look to see how we can define damp. Well, we may define it as where there is water in sufficient quantities to cause problems which may be unacceptable, timber decay, staining, decorative spoiling. However, dampness itself is not a health hazard. The consequences, however, of some types of dampness may be, that is, mold growths, dust mites, bacteria, viruses, and other factors. How does water get into a house and where? Well, very common. Roof leaks, condensation, plumbing leaks, condensation in the main part of the property, lateral water penetration from high ground levels, flooding, subfloor condensation, rising damp, defective rainwater goods, rainwater penetration from the outer fabric of the building, and indeed all those sources of water are unwanted. Visual evidence of dampness, well, there's a whole list and I'm not going to read them all. Mold growth being one, timber decay, eruption of finishes, etc., etc. And dampness to finishes. However, let's get down to the nitty-gritty. How is water distributed in building materials? First of all, we're going to look at masonry. And by masonry, I'm lumping together here brick, mortar, plaster, and so forth. The total moisture content of a material is potentially the sum of two components. The first component is known as the air-dry or hygroscopic moisture content. And this is what we would regard as a dry material when there is absolutely no water ingress. It's a material standing level of moisture when in equilibrium with the air. Remember, no water ingress. The second component is known as the capillary or free moisture content, and that is moisture that fills the capillaries of the material. This is the fraction which is only present where there's an active source of water ingress, e.g. rising damp, etc. And it's usually, but not always, this fraction that causes the problems. This is the water that is usually unwanted. And looking at the distribution of moisture in masonry, let's start off by looking at, say, a small piece of brick. That small piece of brick has a pore present in it. So we've magnified it enormously. This small piece of brick has been in an oven and it's been dried out, completely dried out, absolutely as dry as a bone. The minute we take it out of the oven and suspend it in air, water is simply absorbed from the air. And this is where we get our hygroscopic or air-dry moisture from. And that is how it will stay. It will vary slightly depending on the humidity. However, if we then come along and start pouring water over our piece of brick, then the pores start filling with water, and this is where we get our capillary moisture from, capillary or free moisture. As long as we keep pouring water over our piece of brick, we will maintain capillary moisture. However, if we stop it, suspend it in air, then it will simply evaporate and we come back to our standing hygroscopic moisture, our air-dry moisture content. And that's where we hopefully find a dry material. However, the only way we will maintain a truly dry material is to put it in an oven and heat it. And that's where we will get back to our purely dry material. Hydroscopicity of air-dry materials, examples of uncontaminated masonry. Well, let's have a look. There's just some examples. We've used here an air-dry moisture content measured at 75% relative humidity. Gypsum plaster 0.4, red brick 0.3, cement render 1.3. It's usually higher if it's not carbonated, lime plaster 1.5. They're not fixed, they will vary. It does depend on the material. Indeed, some lightweight renovating plasters are up to about 6%. These are clean, air-dry materials. However, as we'll see later, if we contaminate those materials with certain salts, hygroscopic deliquescent salts, then our air-dry moisture contents, even at 75%, can increase massively, sometimes making the material actually look visibly damp. But as I've said, we'll look at this again later. And this just illustrates what happens with an increase in relative humidity. It increases the air-dry moisture content. How much it's going to increase, it depends on the particular material. What do we therefore mean by the term saturation? Because we're looking at moisture content. We say a material is saturated. Well, let's have a look at this. This is a material. The black lines are the pores in the material. This is both porous and permeable. The material, in this case, is saturated at a total moisture content of 16%. It has moderate porosity and permeability. However, this material has limited porosity and permeability. That is saturated at 5% moisture content. All the pores are full of water. It can't take in, neither of those can take in any more liquid. Yet they are, in many respects, equally as wet. They are both saturated. And taking this a little bit further, let's imagine this is a brick embedded in mortar, and it's been raining for 40 days and 40 nights, and water's been running down the wall. The brick is saturated at 10%, the mortar has become saturated at 16%. The minute we stop the water, we fix the water leak, things are going to start to dry out. And we would get to a hypothetical situation where the brick is half saturated at 5% and the mortar half saturated at 8%. Where we're going with this is that it is an error to try and compare the total moisture contents of two totally different materials. They will have almost certainly different moisture carrying capacities, different saturation values. One common error is as illustrated here. Somebody's measured the plaster and find it's got 7%, and then they've taken a sample of the brick and find it's only got 4%, and they conclude that the problem isn't dampness in the wall really, it's due to something like condensation because the plaster is wetter than the brick. One cannot make that direct comparison very, very easily at all. So we've looked at the distribution of water in building materials, that's masonry. Let's have a look at wood. There we go, the equilibrium moisture content of wood. The important feature to remember about wood is that it is a hygroscopic material. It absorbs moisture from the atmosphere. Its air-dry moisture content depends on the surrounding humidity. And there are a couple of examples. Say in our example there, wood kept at 80% RH has a moisture content, air-dry moisture content of around 18, probably 19%, probably a bit more in some cases. However, if we drop the relative humidity down to around about 45%, then our wood will come out with a moisture content, an air-dry moisture content of 10 to 11%. Wood is a hygroscopic material. And this is just a more complicated version of the same table, more accurate clearly, but it does show that there is a temperature factor. And we do get very high humidities as standard in colder months of the year in cellars, subfloor areas and roofs. So then, how is water distributed in wood? Well, if we imagine wood being made up of little boxes and tubes of, say, cellulose, the first thing that happens is that the cell wall takes up water first. And the cell wall becomes saturated at figures around 28 to 30% moisture content. When the cell wall is saturated, it is said to be at its fibre saturation point. And indeed, on some of the older moisture meters, as we'll see later, this is marked. However, if there is an excessive source of water, then water starts to fill the boxes and the tubes itself. It starts to fill the lumen, and this is where we get moisture contents in excess of 28 to 30%. This is where the wood now starts to become wet, and it's really at this stage it becomes excessively vulnerable to the development, initiation and development of fungal decay. Dampness in Buildings and Diagnosis, Module 2. Measurement of moisture. Again, masonry, brick, mortar, plaster. So let's have a look at the instruments that we have for the measurement of moisture, and we'll start looking at electrical moisture meters. Radio frequency meters, basically also known in some meters as a search mode. Basically, they measure the capacitance of the substrate or send radio waves into the substrate. These have an advantage of looking, for want of another word, deeper into the substrate, probably up to 12-15 millimeters as claimed. However, there can be a problem in as much as they do not appear to be particularly sensitive to surface effects only. The capacitance meter, like the radio frequency meter, the capacitance meter will identify problems below the surface. However, probably the most common meter is the resistance or the conductance meter, and these measure the electrical resistance of the substrate between two electrodes, two pin probes. Some people call them pin meters. So then, when used on masonry substrates, electrical moisture meters do not record percent moisture, and they do not record percent saturation. They simply record a relative reading not directly proportional to the quantity of anything. They are purely qualitative. Also note that they do not respond to any significance on most uncontaminated materials in their air-dry state. There are very, very few exceptions. Moisture meter scales. All meters have them. This is quite an old meter. It's about 40 plus years old, and we can see the scales. There are two timber scales at the top and a masonry scale, or rather a relative scale along the bottom. That particular one is calibrated from 0 to 100. Anything over 15-16% full scale deflection is covered in red, which suggests in this case it could be a problem. Later meters, LED meters, single scale meter. There's the scale, and it's a wood scale. But we also get the pretty colours, green, yellow and red, to help us on masonry substrates. Again, the later meters are exactly the same. A timber scale, that's an LCD scale, and we have the pretty colours again to help us on a masonry substrate. So what's then the relationship between the timber scale and the relative scale? Well, if we go back to the old meters, the old analog meters, we can see this. And here's two examples. On the bottom we have 15% full scale deflection, or 50% full scale deflection as another example. And if we look and project those to the timber scales, we can see that, funny enough, that figure happens to match the 20% figure, a figure that people regard as vulnerable for timber to be at fungal decay. Again, 50% full scale deflection on the bottom scale, the relative scale, corresponds to 25-26% on the upper scales. The interesting thing to notice about these older moisture meters is they are not calibrated about above 28% moisture content, simply because 28% roughly is the fibre saturation point, and moisture contents above that basically go haywire. They're very, very inaccurate. So when using a timber scale on masonry, the result should be expressed as percent wood moisture equivalent, percent WME. Note, however, the term wood moisture equivalent is supposed to represent the moisture content of wood if in contact with the particular masonry substrate. There has never been any evidence to support this. Thus, in reality, the term simply shows that a timber scale was used on a masonry and nothing else. So let's look at the scales themselves. Qualitative colour scales for use on masonry. The manufacturers say, and this really goes for all manufacturers, green no problem, yellow further investigation or remedial works, red remedial action required. In reality, these interpretations are generally too low for masonry substrates. Probably a better level for the beginning of significance on masonry substrates would be 24-25% WME, or in the case of the radio frequency meter in search mode, 240 to 250. Those would be better. These meters are very sensitive on masonry substrates. We could, however, use insulated probes. These are simply plugged into the meter and they are insulated except for the very end where you can see there to the left the electrodes are just protruding. Can be very useful. And the use of deep probes, here we have a wall that has a damp contaminated surface. The fundamentals of the wall are dry. If we use steel pin probes, then clearly we're going to get a response because they respond to the surface. So what we can do, we can drill a hole through into the wall and place our insulated probes in there where they will not prove to be a problem because the insulation protects them from the potentially damp contaminated surface. Just a comparison of surface moisture meter responses, resistance versus radio frequency, for example. There we go, the columns, resistance and radio frequency. Condensation, yes, on resistance, limited on radio frequency. Condensation, deep probes, nothing. Obviously assumes the walls clean and dry. Radio frequency, not really applicable. Salt contamination, both will respond to hygroscopic salt contamination. Rising damp, yeah, they both respond, but you have to be a bit careful with reference to a radio frequency or capacitance meter because they are reading beyond the surface. Indeed, the surface may be dry. So do not use those meters to evaluate the performance, for example, of a previously installed chemical damp-proof course or retrofit damp-proof course. They will pick up water and salts beneath a dry surface. Penetrating damp, yeah, they'll both pick that up as well. So what are the problems we get with electrical moisture meters? Well, first of all, as we've seen, they are too sensitive. But the other feature of them, it takes skill to interpret the results and knowledge and a bit of common sense. So we can get erroneous results from the following. Contaminant salts, hygroscopic salts, they're always present in long-term rising damp to a greater or lesser extent. Also present around some chimney flues by means of burning, long-term burning of fossil fuels. Some materials containing carbon or other electrically conducting material. That's pretty rare and it's also local knowledge usually. Foil back paper, that's good. Clean surface, paper surface, no problem at all with the wallpaper, no visible problem. Stick the moisture meter in it and it goes haywire. But again, that's experience. It's likely to be foil on the back. One can check it, but then you've got to ask yourself, why is the foil there? Degree of contact with the probe, that depends on all types of meter. Doesn't matter which type, the probes have got to make good contact. Results on masonry can vary significantly with the type of meter. You cannot easily compare one meter's individual figures with another, at least on the relative scale. One has to be careful, that's all. And of course, if you stick your fingers on the probes of a pin type meter, you can get some really, really good readings. However, if you think about it, over 99% of high figures will be the result of water and or hygroscopic salts in the substrate or the material, neither of which should be in the masonry and must therefore have arisen from somewhere. So how do we use an electrical moisture meter? It must not simply be stabbed at the base of the wall around the room and making the diagnosis. The wall must be vertically profiled. You need a pattern of meter readings taken over the wall, certainly in vertical profile, or some people may require a pattern over the wall, vertical and horizontal. Vertical profiles, whatever their figures you're using, should then be interpreted based on the knowledge of what the meter is responding to. The important feature is, and it can only be emphasized, is the pattern of the profile, which leads to a potential diagnosis. And of course you've got to add common sense to the whole thing and a pair of eyes. So how do we interpret these moisture meter profiles? Then let's have a look at a few. The patterns above, or rather below, have been validated by other methods. So here we have some patterns, A to F. The red readings are considered to be significant, and the asterisk identify really a salt band. So what's pattern A? Active rising damp. Very high meter readings up to, in this case, a meter, can be higher, maybe a bit lower, where we then get a sudden cut-off of the readings. That is typical of active rising damp. Possible interpretation. Before we go on any further, however, we need to have a look at the distribution of groundwater salts in rising damp. There they are. There typically is a distribution, ideally, and we have low levels, trace, sometimes no significant levels at the base of the wall, rising to the maximum height of rise, where we get the high levels of salts, the greatest levels of salts, where they form a salt band. And indeed, it's the salts that show us the maximum height to which water once rose. If water, for example, rises higher, then the salts will go up with it. However, if the wall dries down, the water will dry down, but the salts will remain put. So therefore, they effectively give us the history of the rising damp. And remember, the important thing to remember as well is such salts will cause a moisture meter to respond. So back to the interpretation of the moisture meter patterns. Let's have a look at pattern B. What have we got here? Some low readings at the base of the wall, and then they start to increase, in this case up to 1250 millimeters, and then disappear. Possible interpretation, we call that, well, I rather call it fixed rising damp. In other words, the walls had rising damp, but it's dried down. And what we're now getting is simply the results of the salt contamination. Pattern C, it's a bit of an esoteric pattern, this. High readings declining and then going up a bit. So I call it part-controlled rising damp. The lower levels of figures are due to water, and as the water declines, the figures decline. However, the wall has dried down to a certain extent, but above that we've still got the salt problem. You'll see this better in the next diagram. Pattern D, low levels, figures simply over the skirting at the base of the wall. These represent possibly a floor wall junction problem. Pattern E, no readings at the base of the wall. It's probably been re-plastered, and the plaster work is doing exactly what it's supposed to do. Dry, surface, uncontaminated surface, hence the low readings, but the DPC is not effective and it's come up over the top of the new plasterwork, or it was never replastered to sufficient height in the first place. Pattern F, well, we usually call it the damp proofer's nightmare. These are the actual profile patterns, and I think they're very much self-explanatory, where we're looking at the water, the distribution of water and the distribution of salts. The interesting one, it's not covered previously, is pattern F, where we've got some high-ish readings at the base of the wall, and they tend to decline as we go right the way up the wall. Possible interpretation of this is high humidity on wallpaper. In other words, the meter is simply responding to the hygroscopicity of the paper. So these are some moisture meter profile patterns. And here's some moisture meter responses to salts only. Deep probe readings. We can see there the deep probe reading, and we can see, we've just put them as a star pattern, the level of salts, chloride and nitrate, two profiles. And the high readings are given in red. But if we look at this pattern here, you can see in broad terms, the higher the moisture meter reading from the deep probe, the more salts are available. This is a sort of a simple graphical relationship. You can see basically there is a sort of a relationship between salt levels and the response of a moisture meter, at least based on that previous data. Other modes of use, moisture mapping, useful for plotting areas. And there's a moisture map. That one was actually done in both the pin mode and the search mode. Interestingly, the figures in red are slightly higher, but analysis, gravimetric and salt analysis showed there wasn't a problem. They are actually dry figures, no salt contamination. Just shows how sensitive these moisture meters are really to some really what I would loosely call non-problem. Potential tests for surface effects only, we saw that earlier on. Damp surface, insulated probes. The probes are isolated from the surface effect. Really, however, if you're going to look at atmospheric moisture, say condensation problems, these should be investigated by the appropriate means, such as looking at relative humidity, surface temperatures and dew points, rather than trying to use a moisture meter. Again, other modes of use, potential tests for surface finish versus substrate. Again, using deep probes. Here, this sort of method is especially useful if you're dealing with a wall that you believe is possibly dry, but contains electrically conducting materials, whatever they may be, whereas the surface could be itself dry. This can be shown by pins. Probably the most common problem here would be a wall that's been damp-proofed, but the surface is shown to be dry by means of pins, whereas the deeper in the wall, using deep probes, you've got high readings. And of course, this is where we have problems with RF meters and so forth. They cannot distinguish this and could lead towards a misdiagnosis. Further tests may therefore be required. The problem here is the meters are responding to what's deeper in the wall rather than what's on the surface. Other modes of use, also check any timbers where in direct contact with masonry. You need to put the meter as close as possible to the potential source of dampness. In the case of a skirting, this would be at the very top or the very bottom, and make sure there are very good probe contacts. The reason for this is quite simply water does not pass across the grain of the wood very well at all. So you need to go at the thinnest parts of the timbers where they are in close contact with the substrate. Obviously, this depends on the skirting not being isolated from the wall. Finally, it's very important to appreciate that an electrical moisture meter is an essential tool for damp surveys. It is not, however, an absolute instrument for diagnosis, but used intelligently, knowing its limitations, and in conjunction with visible assessments and other observations, they will form a very important aid and guide to the diagnosis of dampness. This is very important where one is dealing with and has to undertake a non-destructive investigation. Dampness in buildings and diagnosis. Module 3. Measurement of moisture. Again, we're dealing with masonry and we're looking at gravimetric analysis. In other words, you've got to weigh it. It is known as the oven dry method, and it identifies total hygroscopic air dry and free or capillary moisture. That is the full quantitative distribution of water in masonry. Its importance of such full distribution is emphasised in building research establishment Digest 245, Rising Damp in Walls, Diagnosis and Treatment, where it states, experience has shown that some building materials possess a hygroscopic moisture content, air dry moisture content, of up to 5%, even without the introduction of salts from external sources. This emphasises the importance of the difference between the air dry moisture content and the total moisture content measured on samples. So how do we do it? First of all, we need a balance, a 3-figure balance, a milligram balance. Samples collected by means of a slow speed drill and put in an airtight container immediately. This prevents moisture loss before the analysis and allows them to be taken from site back to your office. We then weigh the samples. Ideally, as mentioned, they should be dust-like, but you can use small pieces, but it just takes longer. Number 2, put the samples into constant air dry conditions. The problem normally is if you leave them in the open, the humidity in the open varies enormously, or it can do. So we want constant air dry conditions. And for convenience, these are set at 75% relative humidity. We leave them there for 2 to 4 days to come to equilibrium. We can use higher or even lower relative humidities. This is done by changing the salt solution, which maintains the humidity in the chamber. We then weigh again. And the principle is very simple. If the sample loses weight, it dried out. In other words, the drying, it contained capillary or free moisture, and it was therefore subject to water ingress at the time of its removal. If the sample does not change in weight, sometimes it'll gain, it was dry, not subject to water ingress at the time of its removal. Finally, we dry the sample at 50 degrees and make a final weighing. And we now have all our figures, and that is the complete procedure summary. Total moisture, hygroscopic or air dry moisture, one minus the other, total minus hygroscopic, gives us the free or capillary moisture content. And of course the capillary moisture content in a material indicates the source of water ingress. If we take this to a practical level, we can sample for moisture and also make a salt profile. This is done by a vertical series of samples on which we do total free and hygroscopic moisture. If we look at a wall, for example this wall, we notice the bottom is damp and the top is not damp, or at least visibly damp. If it's rising damp, the groundwater salts will be present as well as moisture if it's active, but above a certain height there will be no groundwater salts and it'll be dry. And indeed, it's the presence and distribution of groundwater salts that are almost unique to rising damp. And indeed, the presence and distribution of the salts in relation to the presence of moisture are the major keys to the diagnosis of rising damp. And in essence, we really need to determine both. We can also use the method for other than rising damp, as we'll see. As mentioned just now, the method is particularly powerful for evaluating rising damp, but especially the performance of retrofit damp-proof courses. And if we're going to use a method, we need to know a little bit. We already know that the salts mark the maximum height to which water is risen, and if it rises further, so do the salts. But, just as a recap, if the wall dries down, the salts don't move, basically. They remain at the maximum height to which water once rose. So we can use this comparison between the free moisture presence and the salt presence. The drawing on the left shows a non-effective DPC. There's free water present to the height of the salts. The centre diagram shows salts up to a given height, but there is only water rising now to a much lower height. Therefore, that water has dried down from the original height as indicated by the salts. The third example is where we've got salts to a certain height, but we have free moisture rising above this. This indicates there's a further source of water ingress, i.e. free moisture above the height of the salts. Exactly how effective a damp-proof course would be in that situation, we don't really know, because we don't know how much of the water at lower level is still due to rising damp, or how much of it was due to the water penetration. So let's have a look at several case studies. Here we have a moisture and a salt profile. Let's see what it tells us. There we go. We know that salts, or rather the rising damp, has risen to around 1200 millimeters in the past, as indicated by the maximum height to which the salts are present. However, we still have free moisture rising up to the same height. They're both at 1200 millimeters. In this case, we've still got fully active rising damp. There has been no control of the rising damp by the Retrofit damp-proof course. In other words, it didn't work. Another case study. There's one of the several profiles that were drilled, and the complaint was that the damp-proof course wasn't working, therefore the damp-proofing company should come back and do it all again, etc., etc. In this case, however, the client did not want any replastering. No, he didn't want any of the replastering. He was told it should be replastering, and this was well covered in the documentation. So we have this result. We know that rising damp in both of those profiles once rose to somewhere about 500 millimeters. We've seen it in the brickwork, but especially in the plaster. So we know that it once rose to 500 millimeters. However, there's no free moisture. Those materials are dry. There's no water ingress, nothing. In other words, the damp-proof course has worked. The problem was, of course, the contaminated plaster, because he could see some slight staining in that plaster, which he did not want removed. So here is one where the damp-proof course has worked. Another interesting one was this 16th century hall. There about 9 or 10 of these profiles were undertaken, and it showed that rising damp had once risen to 1250 millimeters. However, when you look at the complete profile, we've only got water now rising to 250 millimeters. It had dried down quite significantly, and this happened in all the profiles. So in this case, there was a proposal to put in a physical damp-proof course of many thousands of pounds for this protection. However, the data did not suggest this. It showed basically there was no problem. It was an old salt problem caused by many, many years of rising damp, which was no longer active. No DPC required. Last one of these is an old external wall 1830s terrace house, been damp-proof course. Salts show that water had once risen to 1750 millimeters. However, when profiled, it showed free water present to 1500 millimeters. It had only dropped a slight amount from 1750 to 1500. For practical purposes, this damp-proof course was not effective. The odd one here, you can see this one. We've got free moisture well above the height to which rising damp once rose. Rising damp once rose to 1500 millimeters as indicated by the salts, but we've got free moisture to the full height of the wall, or as far as we could drill in that wall and get samples. But what have we got then? Well, we know that rising damp once rose to 1500 millimeters, but we've got free water well above that. What we're looking at now is we have another source of water ingress. And when examined outside, there was a small box fitted to the wall. Couldn't see any water run marks from it, but clearly when it was raining, water was collecting behind and penetrating the wall. So in this case, we don't exactly know how much water was coming from the rising damp and how much was coming from the water penetration, because we don't know exactly how much water at the lower level was penetrating or running down the wall or into the wall. Finally, we go to this one. It's another use of the gravimetric method with salt analysis. Chimney breasts in the bedrooms, first floor bedrooms, and you can see there's staining. There was damp staining all around the chimney breasts, and it was thought that there was water penetration coming around the chimney, flashings, pour pointing, etc. They had paid quite a lot of money so far to try and fix the problem, but it was never fixed. We still got this staining. So some random samples were taken, and this is what we got. Front bedroom, rear bedroom. There are more samples than this, but there we go. We have salts present in both samples, but we don't have any free moisture. Thus, there is no water ingress. The problem was the salt contamination around the chimney breast. Where did it come from? Long-term burning of fossil fuels. And this salt had migrated from the masonry around the chimney breast into the finishes. And these are hygroscopic salts, but once they get into another hygroscopic material like wallpaper, then it really does show up as dampness and visible dampness under conditions of higher humidity. Note, especially in the first one, or rather particularly in the first one, there's a lot more chloride than nitrate. This is typical of the long-term burning of fossil fuels, what you may find around the chimney. Note, as I said earlier, there is no water ingress. They spent rather a lot of money on fixing things that didn't occur. And this is visible dampness externally, caused solely by hygroscopic or deliquescent salts derived from long-term burning of fossil fuels. You see where the two chimneys flues are. Shoved up very well. The last meter we are going to look at is the Carbide meter. We've looked at the gravimetric method, and this effectively is a gravimetric method. You weigh things. And this is how the Carbide or speedy meter comes in a box. The meter, scale to weigh the sample, 6 grams, can use a 3 gram sample and double the result, and the reagent. The speedy reagent is calcium carbide, and that's put in one part of the meter. You see the meter in two parts with an O-ring, and a 6 gram sample is weighed out, a dust-like sample. It must be dust-like, and put in the other part of the meter. The meter is closed and intermittently shaken to mix the materials. And the principle is quite simple. Calcium carbide, a speedy reagent, reacts with water in the sample to produce acetylene gas. The more water, the greater the volume of gas. The system effectively is a sealed system, so the more gas, the greater the gas pressure. And therefore there's a direct relationship between gas volume, gas pressure and moisture content. And there is a pressure gauge on the base of the unit which is calibrated for total moisture content by weight. And that's the scale. So then, what are the problems with carbide meters? One, they're very slow to use. They take about 10 minutes of sample by the time you've shaken up, left it, shaken up and left it to get the reading. They're messy. You've got to dispose of the carbide powder. And the other little problem with them is they're used on site usually, and they can cause the user to give an instant response, which may not be helpful. Frequently the client is looking over the investigator's shoulder when this is going on. The investigator is expecting something, but it comes out, let's say, much higher, and usually that's where the instant response has to come in. If you're going to do such on-site testing, then ideally drill your sample out, put it in an airtight container and take it back to the office and do it. You've got nobody sitting over your shoulder looking. And on site, the other problem with them is they only measure the total moisture content. The results could be air dry alone. Capillary moisture, hygroscopic moisture cannot be undertaken on site with a carbide meter. You can only determine the total moisture content, and this can be a problem. Indeed, that's what happened in this case. This was profiled, believe it or not, with a carbide meter, the full profile, and you can see the total moisture contents very high, up to about 900 millimeters. So the view was the damp-proof course had failed. The retrofit damp-proof course had failed. However, when we did a full gravimetric profile, when that was undertaken, it showed from the salt analyses that dampness had once risen, rising damp had once risen to about 900 millimeters. But the capillary moisture content, free moisture, water, was only present at 100 millimeters, quite high. At 100 millimeters was the actual height of the damp-proof course, so that would be expected. Above that height, the wall was technically dry. There was no water ingress. The high moisture contents obtained in the total moisture content were indeed hygroscopic moisture. This was due to the presence of the high levels of salts. So in this case, the damp-proof course had worked pretty well. The problem was not any longer a rising damp problem. It was a salt problem. A salt damp problem. And the other error that you can make comparing different moisture contents of different materials is quite simply, we've seen this before in one of the earlier modules, different materials have different permeability and porosity, and there's our example of 7% in plaster, 4% in the brick, and if one is attempting to make those sort of comparisons, they can really lead to misleading results and inaccurate conclusions. However, all is not lost. If one reads BRE Digest 245, then that identifies the correct use of a carbide meter. And this simply requires you to take, or the investigator to take, double the sample. Put it in your airtight container, take it back to your office. When you're back there, put your normal 6 grams into the meter, shake it up, leave it. That will give you our total moisture content. The second part of the sample is put into our constant humidity chamber at 75%. The figures there should be lower than that. We'll use, say, 1 to 3 days, depending how many samples in the chamber. So we've got our sample. It's gone into our 75% RH chamber for a period of time. We then weigh out 6 grams of sample into the meter, shake it up, leave it, and this will give us our air dry or hygroscopic moisture content. We then go back to our simple equation. Total moisture content minus hygroscopic moisture content is the free moisture content. So we now know exactly how water is distributed in that particular sample. Dampness in buildings and diagnosis, module 4. Measurement of moisture in wood. The equilibrium moisture content of wood. It's important to appreciate that wood is a hygroscopic material. It absorbs atmospheric moisture. The level of atmospheric moisture taken up depends on the surrounding humidity. For example, at 80% relative humidity, we would expect wood to have a moisture content simply from water absorbed from the atmosphere of probably 18–19%, getting up towards 20. On the other hand, if we could maintain the wood at 45% relative humidity, we would expect an air dry moisture content of the wood in equilibrium with the air at that relative humidity to be somewhere in the order of 10 or 11%. It should be appreciated that there is a direct relationship between the moisture content of wood and electrical resistance and capacitance as used by some of the meters. This is true with timber moisture contents up to the fibre saturation point, around 28 to 30%. Up to this point, electrical moisture meters are considered suitably accurate, that is, around plus or minus 2%. Above the fibre saturation point, the accuracy disappears. Remember that above the fibre saturation point, the wood is starting to become wet and the lumen of the cells is starting to fill with water. It must also be appreciated that using a moisture meter, there is no such relationship when used on masonry substrates. Hence the term wood moisture equivalent. That is to say, 18% measured in timber is a quantitative objective figure. The same figure on a meter in or on masonry, measured as wood moisture equivalent, is not quantitative. However, what one must remember and appreciate, as shown in earlier modules, is that it's the pattern of readings, if these things are going to be used on masonry, that's important, not the actual figure. Moisture meter timber scales. On the left is a very old meter and it has two scales, softwood and hardwood. And also note that it is not calibrated, for want of another word, beyond 28%, i.e. it is not calibrated beyond the fibre saturation point. How do we use a moisture meter on timber? Basically, we have to measure as close as possible to the potential source of moisture. Take this skirting, for example. We're using the very top of the skirting. Why? It's very close to the potential source of moisture. The feature to remember is that water does not pass very readily across the grain. Hence, you need to go very close to that potential source of moisture. If we look at conditions in a normal dry living environment, we wouldn't expect to have the timber moisture content much above 16%. If it is higher than this, it may be in contact with dampness. So, and I emphasize, as a very broad guide, 17 to 18% moisture content, it might be in contact with dampness, but unlikely to rot. 18 to 20, almost certainly in contact with dampness, although not yet a significant risk to rot. Greater than 20%, in contact with dampness, will be at risk to rot. However, in reality, it is greater, i.e. above the fibre saturation point, to initiate rot. However, for practical purposes, I would use the 20% figure as the critical level for rot to develop. Why? It gives a very good margin for error. However, as a reminder, where high relative humidities may be persistently present, namely 80% plus, and these you find in roof spaces and subfloor voids in the colder months, one may expect moisture contents in excess of 20% due to the hygroscopic nature of the wood. Bear that in mind. So how can we use a moisture meter? Well, let's have a look at this simple one. It's called Follow the Trail. Imagine we're looking at a centrally heated property and the skirting is found to be 19%. What action do we take? Well, what is that suggesting? If the skirting is fixed to a wall at that moisture content, then it's likely that the wall itself is damp. However, if it is damp, The real problem is where it's damp, and is it damp or even more damp lower down in the wall. Now the problem we have here is if that wall is damp, as suggested by the skirting, then we need to look at areas in the subfloor where timbers may be in contact with such dampness. And of course, if it's high enough, it may lead to rot, or the wood may already be rotting. We could also use hammer electrodes for this. And that's a hammer electrode. It's got insulated pins, and you can see the handle part for ramming this into, for example, a floorboard. So we could be looking at a subfloor void in the possible way. We put our moisture meter probes, we ram them in the floor, and on the top of the board we get 13%, say, in our hypothetical example. However, by the time we've rammed those moisture meter probes through the boards, you get a much higher moisture content. Now that starts to suggest a humid subfloor, possibly even damp, so it would indicate that it does perhaps need investigation. So that's the method using a moisture meter. There is another method, of course, and that is the oven dry method. And this is quite simple. Basically, one takes a piece of wood, weighs it, and then dries it in an oven at 105 degrees and weigh it periodically until the weight loss is no more than 0.1% between weighings. The reason for this is quite simply, once you start drying wood, it continues to lose weight, even tiny bit by tiny bit. So that's what we're looking for. If that weight loss between two weighings is less than 0.1%, we call that the final weight. So we then come to the calculation. That's the wet weight of wood, i.e. its original weight, minus the dry weight, and that gives us the weight of water, over the dry weight of wood, times 100, will give us the percent moisture content by weight. The next section is on the measurement of moisture in air. It's simply a very short section to cover the methodology, just outlining it, but more examples of this and how to use it properly are given in later modules. One method of looking at atmospheric moisture, i.e. measuring the relative humidity, is a whirling hygrometer. It's rather like a football rattle, where we have two identical thermometers. The top one is known as a dry bulb, and the bottom one is known as a wet bulb. This has a wick around it, and this wick leads into a little reservoir of water. The idea is you swing it around your head, allegedly at a lot less than 2 meters per second, and we get two readings. We get the air reading on the dry bulb, the room temperature reading on the dry bulb, and the principle of the wet bulb is quite simply that when evaporation takes place, it cools the surface of that material, and it will cool the bulb at the base of the thermometer. So we finish up with two different readings. The more humid the air, the slower the rate of evaporation, and the lower the cooling. The drier the air, the faster the rate of evaporation, and the greater the cooling. So, as I've just mentioned, we finish up with two temperatures and a difference between the two. We can look at that difference between the two and check them on a table or a set of scales, and this will give us the relative humidity. From this, we can also calculate the dew point. Thermo Hygrometers in general, the one on the left is a little handheld Thermo Hygrometer, very good for snapshot surveys. That is a survey when you're in the property. However, these handheld instruments must be allowed to come into equilibrium with the environment before taking any readings. If they're not, and you bring it in from a very cold car into a warm building, you'll get silly readings until they come down to room temperature. Most of these meters will also record the dew point temperature. The little gadgets on the right are simply little thermohygrometers which can be left in the room for the occupants to see the temperature and humidity data in real time. Finally, we have data loggers. Atmospheric data loggers, and these are used to sample atmospheric conditions over a period of time, e.g. 4 weeks plus. They can monitor for over a year depending on the time gap. The beauty of a data logger is that in a building, the atmospheric conditions can change very rapidly during the day and during the night. Even within relatively short times, we can get rapid changes. The problem we have there is if one does a snapshot survey, which is frequently done, then half an hour later, the conditions can be totally different. So that is the beauty of data loggers. These particular data loggers, as probably many of them do, they record temperature, humidity and dew point at set specific time intervals. And these can be used to calculate other factors. With reference to moisture in the atmosphere, we'll look at this in more detail and interpretation of data in a later module. Dampness in Buildings and Diagnosis, Module 5. Salts in Building Materials. Efflorescent salts. Efflorescent salts form on surfaces, including beneath wallpaper, paint films and plaster. The latter they can literally blow off as they form. They form as a white, amorphous powder or a crystalline solid. Whether they form as a powder or a solid depends on the surrounding humidity. Most are sulfates, usually sodium sulfate, but as we'll see later, one can get magnesium sulfate in certain roof tiles. And sulfates are common in many older building materials. The important thing is they lose water to the air as they form on surfaces. They lose water. And where visible, they indicate the passage of water through the material. It's very important to note that salts can only move in solution, not as a solid. Crystalline deposit of efflorescent salts on new plaster is a good example of it there. And just one point about efflorescent salts. They alone, in the absence of moisture and any other form of contamination, will not cause an electrical moisture meter to respond significantly. Here they are, forming on the surface of a render, and they are literally cracking and blowing off the plaster finish. The other group of salts in building materials are hygroscopic salts. Hygroscopic salts absorb water from the air, but they are rarely visible as deposits on surfaces. However, their effects are in the form of visible dampness and high surface moisture meter readings. And indeed, where they result in visible dampness, this is frequently referred to as salt damp. Do not confuse efflorescence with hygroscopic. We've seen reports whereby the investigators stated that hygroscopic salts were visible all over the surface. No, they weren't. They were efflorescent. Uptake of moisture from air by hygroscopic and deliquescent salts. The absorption of moisture depends on several factors. Number one, the humidity. The greater the humidity, the more water that's taken up from the atmosphere. It also depends on the particular salt. Some hygroscopic salts are more hygroscopic, for want of another word, than others. And of course, the amount present. The more the merrier, basically. Low levels of hygroscopic salts don't usually cause visible dampness, but they will still record high electrical moisture meter readings. So this is very roughly a diagrammatic form of the relationship between the air-dry moisture content, i.e. the hygroscopic moisture content of a material, and the humidity and level of contamination. Low levels of contamination, as we increase the humidity, very little happens. It'll go up slightly, as indeed it does in a clean material, but it goes up a little bit more. However, look what happens when we get heavy contamination. In a low humidity, it's probably not noticeable. There is more absorption of water from the air, but when the humidity is high with heavy levels, we get a massive increase in water absorbed from the atmosphere. The highest I've come across is 24%. All that moisture was hygroscopic. So the absorption is related directly to humidity. Where we get dampness caused by hygroscopicity, we refer to it commonly as salt damp. And this appears to come and go depending on humidity. Often appears on rainy days, then dries out. Also common around chimneys. Salt damp can come and go pretty rapidly, often within a few minutes from being visibly dry to visibly damp. If we look at water ingress, however, this usually results in some degree of efflorescence and eruption of finishes, not just simple visible damp. Some examples of salt damp. On the left, the old plaster was left on. This was a job basically that looked pretty clean, but one day it just appeared like that. As the humidity went up, so did that, and that appeared in a matter of a few minutes. The other section on the right, salt damp, that's where dampness is solely due to the hygroscopic nature of the salts. We saw that one in an earlier module, caused by hygroscopic salts being derived from a chimney flue. The other feature of them is if the hygroscopic salts get into a hygroscopic material, such as wallpaper or cardboard, then the effect of dampness seems to be exaggerated. Salt damp on a bedroom chimney area, first floor, and salt damp on a lounge wall. Salt damp, funny enough, seems to look different. Salt damp just looks different. There is an extreme of hygroscopic known as deliquescence or deliquescent. If we take a material that's hygroscopic, or rather hygroscopic salt, increase it in humidity around it, it will become deliquescent. That means to say it can absorb so much water from the hygroscopic state that it will actually start to dissolve in itself. And different salts become deliquescent at different humidities. For example, let's take common salt, sodium chloride. A 75% RH, it's hygroscopic. It goes a bit sticky because it's absorbing water. But increase the relative humidity to 85% and leave it, you will find it starts to become liquid. It's absorbing so much water that it's starting to dissolve in itself. Once deliquescent, it is a liquid, and it can therefore become mobile in and through contaminated permeable materials. So a liquid form can move. This is a good example taken by a friend of mine with reference to hygroscopic salts. He's got two humidifiers. The picture on the left shows two humidifiers. There's not much to be seen, but after 5 minutes you can see where the old chimney was. It's showing distinctly visible damp due to salt damp. It's become visible due to the higher humidity. There's more water being absorbed. Effects of hygroscopic salt contamination. The differences, note, are solely due to the moisture being taken out of the air. And they're the same material, uncontaminated and contaminated. And already I think it becomes evident, possibly, that contaminated, already hygroscopic materials such as wallpaper can absorb a hell of a lot of water. But I will add, the levels of salts in those papers and the other samples were not distinctly measured. However, it does illustrate these differences in moisture content solely due to the hygroscopic salt contamination. Basically, the more contamination, the merrier, the greater the moisture concentration. Look at the high ones like the lime plaster and the cement render. I mean, they would be visibly damp. A red brick at the bottom, the 7-point-odd% would make it look a bit red. It would look distinctly red. Now, I mentioned earlier, the level of moisture absorbed in a contaminated material will depend on the humidity, the salt itself, and the amount present. Quick look at the salts themselves. Chloride and nitrate from rising damp. The amount deposited in masonry depends on several factors. One, the levels of salts within the groundwater. That's just an example from some groundwater around Buckingham. 20 parts per million of chloride and 50 parts per million of nitrate. The rate of rise of the rising damp and the rate of evaporation. The duration of the rising damp. And now, if we're looking at properties without a damp-proof course, we are looking at a long time, over 100 years. Tap water may also contain chloride and nitrate, and it also comes from the ground. However, it's highly unlikely that a mains water leak will be of sufficiently long duration to allow a significant build-up of those salts, and levels in tap water are therefore usually minimal. You can obtain the composition of your local tap water from the local water board. Likely origin of contamination. Origin, rising damp, chloride and nitrate. Seawater, chloride. I don't think there's much nitrate, by the way, in seawater. Chimney flues, chloride and nitrate. Usually a high chloride to nitrate ratio. And we also get ammonium salts. Urine, loads of chloride. And old screeds, magnesite, chloride in those. Magnesite, magnesium oxychloride floor screed on a slab. There's a sample that was removed. Those materials, magnesite, are usually coloured, this sort of off reddish. Those materials will always record high moisture meter readings, even when regarded as dry. But if it gets damp, it'll break down and release magnesium chloride, which is deliquescent. Sulfates. Many sulfates are efflorescent, sodium and magnesium sulfates. Present naturally in many building materials at some level, especially older buildings. Present in groundwater. Some areas this is high. They're also part of a rising damp problem or complex, and they're not hygroscopic usually. There are maps around which show you areas of high sulfate content. Magnesium sulfate is present in some roofing tiles, magnesium sulfate being Epsom salts. Gypsum plasters are largely calcium sulfate, and they can cause sulfate attack in newly applied cement renders and plasters. So, have a look at sulfate attack of cement. Cement is incredibly complex, and the chemistry of cement is also incredibly complex. So let's just simplify it for our purpose. Let's look at the left. The CaAl is calcium aluminate. We call that cement for ease of use, plus sulfate. In the presence of water, when it's highly alkaline, forms the material on the right, ettringite, calcium aluminosulfate. Note the 32 molecules of water tagged on the end. The formation of calcium aluminosulfate causes an expansion of cement of over 200%. The cement expands, loses all strength, and will disintegrate. And if you take a piece of severely sulfate attacked, say, render, drop it in a glass of water and leave it overnight, if it's that bad, it simply just disintegrates and collapses into a muddy pile. Note, sulfate from heavily contaminated sulfate substrates may diffuse into new cement render called sulfate attack. 2. Common origin for sulfate attack is the addition of gypsum plasters to cement-based materials, the reason to get a faster set. And there's such an example. It was re-plastered, rendered. The guy the plasterer had added gypsum to the sand cement mix and it simply expanded and blistered. Finally, ammonium salts. These are usually associated with long-term burning of fossil fuels, and they're frequently found in conjunction with staining from soluble tar compounds. So if we take a sample, shake it up, you get this sort of tobacco-coloured water extract. And of course, ammonium salts are hygroscopic. Dampness in buildings and diagnosis. Module 6. Sources of damp, rising damp. Cases of severe rising damp, and I think these really are severe and exceptional, and there are 3. However, probably more commonly encountered rising damp, and basically this is the stuff I encounter. 2 examples there, you can see these and the damp patches. These are where the damp proof course is not proved effective, basically. This is flooding and not rising damp. The diagram on the left shows the result of flooding. You get these concentric rings. The water rises up in the plasterwork or whatever, and then it dries down, leaving these concentric rings. This particular property had a retrofit physical damp proof course, and there was a flood in the end of the property, and that was fixed and it dried down in stages, leaving the concentric marks. We can define rising damp as the passage of groundwater up through masonry. The water rises through a series of interconnecting pores by a process loosely called capillarity. In other words, the porous masonry simply acts like a wick. A more simplistic view is that if the suction of the wall is greater than the suction of the ground, then water will rise. If not, then water will not rise. Thus, water does not automatically rise where there is no damp-proof course. This, of course, depends on pore structure and other factors. Capillarity and hydrostatic pressure. Capillary movement, water movement in small pores caused by the surface tension of the liquid with the side of the pore. There is no pressure forcing this movement. Rising damp is simply due to capillarity, the material acting like a wick. On the other hand, hydrostatic pressure is the pressure of water exerted under its own weight or gravity. Hydrostatic pressure will force water out of capillaries and the water will collect. Hydrostatic pressure has nothing to do with simple capillarity and does not force water up a wall to form rising damp. How high can water rise? Well, the height is governed by several factors. 1, the pore diameter. The narrower the pore, the greater the height of rise. 2, obviously, pore continuity. The pores must be continuous up the wall. And 3, evaporation, and that is affected significantly by the presence of hygroscopic or deliquescent salts. Indeed, all things being equal, which of course in reality they're not, water will rise to a greater height in a thick wall than a thin wall. This is to do with the surface to volume ratio. In a thick wall, the surface to volume ratio is smaller than it is with a thin wall. Thus, on a thin wall, evaporation plays a greater part. Height of rise continuing. Pore size in bricks and mortar can be as small as 1/1000th of a millimetre in radius. Average 0.1 millimetre. Pore size of that size, 1.01, gives us a theoretical height of rise of around 1.5 metres. Thus, rising damp can rise well in excess of 1 metre, a height frequently claimed to be the maximum. Indeed, the highest level I've come across by profiling gravimetric methods was 2.5 metres. The other thing that's important with rising damp are the moisture pathways up a wall. And if one thinks about it, the mortar beds are usually the only continuous pathway up a wall through which water can rise. In order to move from brick to brick, it must cross a mortar bed, and therefore it would not be continuous. So the continuous pathways are the most important part, namely the mortar beds. So we know from earlier on we get salts distributed in rising damp. Those are groundwater salts. All kinds of materials are present: soluble chlorides, nitrates, sulfates and other mineral salts and soluble materials. And with the rising water over a very long time, usually, we get a build-up of these salts. And the typical distribution, we get a salt concentration at the top of rise, known as the salt band, and no significant levels, typically at the base of a wall. And very important, if you are looking for salt contamination, the result will depend on your sampling position. Common effect of long-term rising damp. Seen this often in walls around villages. We have a salt band. We can see that, this obviously damp band. And if we look at a wall in general that's had rising damp or got rising damp, the lower part will contain groundwater salts as long as free moisture. The upper part will be clean. And indeed, it's the presence and distribution of groundwater salts that are almost unique to rising damp, and it is the key to its diagnosis, the distribution of moisture and salts, and we saw this earlier in an earlier module. Features of rising damp versus condensation, well, there they are. You can do the comparison for yourself. Eruption of finishes doesn't usually occur with normal condensation, although I have seen simply in showers a bit of paint peeling, but I think that is fairly straightforward. And of course, there is very broadly a condensation season, and that is between September and April. But as I say, that is a broad definition. So how do we diagnose rising damp? Well, we looked at some of this earlier on. Use of an electrical moisture meter, high meter readings at the base, slowly declining upwards and the sudden cut-off. There's quite a nice note in the Property Care Association's DP1, use of moisture meter, which states it's not satisfactory to check the performance of a new damp-proof course in a building that has suffered from rising damp. In such cases, salts will be present to a greater or lesser extent, whether the new DPC is effective or not. These salts alone can produce high readings. Well, fundamentally, they shouldn't do if you've got a decent dry lining or replastering system. However, if we're going to use a radio frequency meter or capacitance meter, then remember, these will pick up materials deeper in the wall. So, back on to the diagnosis of rising damp. Again, this was covered earlier. The basic moisture profiles, non-effective DPC or no DPC. Remember, the salts mark the history of the rising damp, namely the maximum height to which it once rose. In this case, the salts and the free water are rising to the same height. Secondly, controlled rising damp. Damp once rose as indicated by the distribution of salts to a much higher position. Free moisture is now only rising to a small proportion of that position. Finally, the third one is we can see that we had rising damp as indicated by the presence and distribution of salts. However, there is water going much higher than the level of salts. This simply indicates a further source of water ingress, in which case you cannot tell how any damp-proof course, if installed, is performing, because one doesn't know how much water at the lower levels of the wall is due to continued rising damp or water penetration. We now come to have a look at retrofit damp-proof courses, chemical retrofit damp-proof courses. They consist of a two-part process. The first is the injection process, and that, and I emphasize this, controls the damp. The second part of the process is the replastering or dry lining, and that is designed to prevent future spoiling. Chemical damp-proof courses are a system, and in essence, the two parts are inseparable. If you require a dry non-spoiling surface, they are inseparable. They should be regarded as a control system in that they control moisture but are unlikely to stop it like that of a physical damp-proof course. Hence the replastering or dry lining to give us a dry, non-spoiling finish. So here's a complete appearance of the two. Physical damp-proof course, complete impervious barrier across the wall. Chemical, a diffuse band of a water repellent or pore blocking agent. There is a British standard relating to chemical damp-proof courses, and that is 6576, Code of Practice for Diagnosis of Rising Damp in Walls in Buildings and Installation of Chemical Damp-Proof Courses. It describes 4 systems. High pressure, these are based on solvent systems. You don't think you really come across them much nowadays. Most of the stuff now is either low pressure, usually water-based systems. There's gravity transfusion used for aqueous-based systems as well. Very rare at the moment. And finally, hand insertion used for injection mortars and thixotropic creams. The latter being by far, I think, in nowadays the most common. So looking at the materials themselves, solvent-based systems, they're applied under high pressure. A silicon resin or polyoxoaluminium stearate, POAS, 4 to 5% in white spirit or other aliphatic petroleum solvents. Those materials are initially water repellent. Water-based systems, they're applied by low pressure or gravity, potassium or sodium methylsilicate in water. Both those materials are initially water soluble. So how do they work? Well, the process takes around 2 weeks to complete. We start off with the siliconate, a water-soluble material, which reacts with carbon dioxide and goes through a process, and we come across the material at the bottom, which is a water-repellent silicone resin. Going on with damp-proof coursing, hand insertion, the silane, siloxane, thixotropic creams, and more recently the silane, siloxane impregnated rods. It's the plastic rod, very permeable, full of the appropriate silane, siloxane. Simply drill a hole and it's pushed into the hole in the mortar. How does water repellency work? This goes for silicon resins, POAS, methyl siliconates once cured, silane, siloxane creams. Basically, water repellents line the pores of a material. They do not block the pores. Usually in the case of the silicon and aluminium based materials, the silicon is bonded with the aluminium is bonded to the surface of the pore, and the methyl groups, the stearate groups, stick out within the pore, and these form the water repellent surfaces. Water repellent action. Water repellents are pore liners. They change the surface tension of liquid with the side of the pore. The contact angle changes and water rise is stopped. On a treated material, the contact angle becomes greater than 90 degrees and water does not rise. On a non-treated pore, the contact angle is less than 90 degrees and water will rise. Continuing with basic damp-proofing materials, hand insertion is the second one. Injection mortar is a pore blocker, and the way this works is that holes are drilled, rather large holes are drilled in the mortar beds down at an angle of about 30 odd degrees, and the injection mortar is put into the drilled holes and the materials diffuse between the holes in the mortar. The material is a siliconate. How does it work? Well, injection mortar basically consists of ordinary Portland cement, sodium carbonate, silica, tartaric acid, the latter being there to slow the set. When mixed, they form sodium carbonate plus silica. The These two together form sodium silicate, which is soluble, that diffuses through and into the mortar beds where it reacts with calcium and form calcium silicate, which is insoluble, and this blocks up the pores in the mortar. Outline of the installation processes, BS6576, high pressure, low pressure, gravity feed, hand insertion, thixotropic creams. These are the basic outlines of the installation: hole diameter, depth, and where appropriate, the pressure and how to apply. All damp-proof courses should be installed not less than 150 mm above external ground levels, and care must be taken to account for any changes in level. And internally, they should be installed as close as possible to a solid floor. Where the floor is a timber suspended type, it needs to be inserted beneath the timbers. If that is not possible, then one must take precautions to protect the timber, because it is now below the DPC. However, full details on the installation processes and conditions are found in the British Standard Code of Practice for Diagnosis of Rising Damp in Walls of Buildings and Installation of Chemical Damp-Proof courses. So how does moisture now move then in bricks and mortar? Well, let's imagine this. First scenario, impervious mortar and permeable brick. If the mortar is impermeable and the bricks are permeable, then water cannot rise. It cannot move out from any bricks at the base of the wall. So we do not get rising damp in such a situation. Alternatively, if we've got impervious brick and permeable mortar, then water can still move and rise because the mortar beds form the only continuous pathways up the wall. It can bypass the bricks. And ideally, all damp-proof courses should be installed in the mortar beds. It is the mortar beds that are the most important. We also have another advantage of drilling mortar beds, and we can drill the holes in the mortar beds, and these break the path, or at least some of the path, of the dampness to prevent it rising. One of the problems with high pressure injection, which now is really more of historic pressure because I don't know anybody who actually uses it, is that when the injection is applied under high pressure, the DPC forms fingers. It does not push out the resident moisture in front of it. It simply forms fingers which follow the lines of least resistance. These, of course, leave holes of resident moisture through which water can still rise. Bridging. Number there, these are taken from Building Research Digest 245, Rising Damp in Walls, Diagnose and Treatment. Some forms of bridging are more important than others. Some are relatively minor and really aren't going to cause much of a problem. Some just simply boil down to a floor-wall junction problem. We often come across problems associated with a cavity wall, dampness at the base, and it's very careful not to put or run straight into the fact it's rising damp. So what are the sort of items one should look at in looking at a cavity wall? Plaster taken below floor level, plaster taken behind damp-proof membranes, plaster bridging DPC, solid floor bridging DPC, floor DPM cut short, DPC or DPM continuity between the two, debris bridging the cavity, water transmission via cavity insulation, high ground levels, damp-proof course not complete through the leaf. Those are possibilities, are the major possibilities. The least likely option is a non-functioning physical damp-proof course. So then we ask the question, how effective are retrofit chemical damp-proof courses? Well, basically, if we look at them and look at them properly, they will do anything between nothing and something. They do not cause negative effects. They'll do something or nothing, anything between that. If there is a specific problem with a chemical damp-proof course, it did not fail. Basically, it did not work in the first place. They're not put in and then subsequently fail. They're put in and just don't work. Chemical damp-proof courses are unlikely to stop rising damp like that of a physical. Furthermore, they are less effective in genuinely wet walls. My experience is the wetter the wall, the less likely they are to be effective. However, they should control the rising water to a greater or lesser extent, so that in association with specialist replastering and deep dry lining systems, a dry non-spoiling surface is obtained. So for all intent and purposes, once we've got to this stage, we have visually a dry wall. Other damp-proofing systems, they're non-chemical, they're not British Board of Agremon certified. There's the electroosmotic system, which are around and are reported to be effective. The other systems basically are atmospheric governed systems, the Shriver system and porous tubes. They work on atmospherics, they require air exchange. Of course, that is enormously variable depending on wind direction and wind strength, and whether anything is on the outside of the wall that can prevent decent air access to that wall. The question that's always asked, do you really need to insert a chemical damp-proof course? If the dampness is only rising to just above skirting, no, they will have no real effect. If it's like that, then the answer is simply to investigate the floor-wall junction. If the wall is distinctly wet, don't rely on the performance of the damp-proof course. Whatever the case, they are effectively a control system, and water is still very likely to pass above the height of the injection. Flooding does not affect the performance of a previously installed damp-proof course either. Is the problem sufficiently obvious to warrant an installation? But considering this, remember, timber in contact with dampness will be at risk to rot. And finally, it is rare for a physical damp-proof course to break down. Dampness in Buildings and Diagnosis, Module 7. Re-Plastering. Building Research Establishments, Digest 245, tells us that where dampness problem exists, it usually leads to damaged internal plasterwork, and the subsequent need for some replastering is part of the remedial treatment. This is to remove hygroscopic salt contamination, stained material, and replace using a specific replastering system to prevent any further movement of underlying contamination to the new finish. In other words, it prevents future spoiling. And indeed, this is irrespective of what damp-proof system is used as a retrofit system. So looking back then at the distribution of salts in plaster, if we've had rising damp, long-term rising damp, we will have, to a greater or lesser extent, some degree of salt contamination in the plaster. And this can affect the decorative finish, even though the rising damp has been controlled. And therefore serious consideration must be given to the removal of this potentially contaminated plasterwork. And here was a problem that turned up. This was a gold wallpaper, not real gold. I think it's a mixture of copper and iron salts. And this wallpaper was put on contaminated plasterwork. And the chappie was not very pleased when his expensive gold wallpaper turned blue due to the salts in the underlying contaminated material. It's very important that the plasterwork can resist the passage of any underlying moisture in the wall from passing to the decorative surface. This is to prevent future spoiling. And remember in this fact, when a salt becomes deliquescent, it becomes liquid and it can move as well. So then, why do we need to look at this? Well, first of all, walls take time to dry out, the theoretical figure being 1 month for each 25mm of thickness, and of course the limitations of a chemical damp-proof course itself. They are only a control mechanism. So replastering for water and salt resistant finishes, we need to use a strong sand cement based mix and a well graded sand. Renovating mortars are, in my experience, not always effective. Lime-based mixes are too permeable, and so are cement lime sand mixes, and all those may lead to future spoiling. And under no circumstances should gypsum-based bonding plasters be used. In some cases, replastering systems may be unsuitable, as we'll see later, and serious consideration must then be given to dry lining systems. So how can we use, or what can we use as a replastering specification? Well, this one has been around for a very long time, and it consists of 1 to 3 ordinary Portland cement to sand, and I emphasise by volume, or as they call it, traditional volume proportioning. The sand should be specified as clean, sharp wash sand, loam free. The mix should incorporate the use of a suitable waterproof or salt inhibitor, and usually there are 2 12mm coats with a finishing coat to finalise. So why do we need a strong mix? Well, let's have a look at this diagram. If we use a mix in the order of 1 to 3, then we find that the cement paste will fill all the gaps between the sharp sand. However, if we use a weaker mix, such as say 1 to 6, then what we find is that whilst the particles are well glued together, there is insufficient cement paste to fill all the gaps, so we get holes present, and those lead to permeability. So we finish up with a permeable mix which may allow water salts through to the decorative finish. The other feature that is important in a sand cement mix is the sand grade. 1 part cement requires only 0.2 parts of water for the chemical set of the cement. More water is required to make the mix workable. The workable water simply evaporates once the mix is on the wall to leave holes, and those holes contribute to permeability. The problem is simply that high fine sand with a lot of clay and silt in it increased the water requirement for workability. Therefore there is more water to evaporate, and this leads to more holes and therefore a more permeable mix. Here's some samples as run through the old British Standard 882 sieves, and you can see the different mesh sizes. The stuff at the top is the good stuff. That is excellent. It meets grade M of that British Standard. The stuff at the bottom is pretty poor. That will almost certainly start to cause problems. It will require, a mix containing that sand will require a lot more water. It contains a huge amount of clay and silt. And they're just the gradings. I'm not going to dwell on these. There's sample A, passing the different sieves, and that's what was required for grade M. That was the good stuff. Sample B, I think, was the bad stuff. It's way out of grade F even, much lower than that. So what do we require in a waterproof or so-called waterproof mix? Well, do we use a salt inhibitor or a waterproofer? Well, basically, they both do the same job. They're designed to prevent the passage of water through the material and therefore the passage of salts, because the salts are in solution. Types used in water-resistant renders, pore blockers such as Seeker 1, I believe they form silicate complexes, plasticizers and water repellents, metallic soaps, organic acid, and bitumen emulsions, which are water repellent. However, We could also use dry lining systems such as these plastering or cavity drain membranes, and they are becoming very popular. Indeed, they are far more appropriate for use in listed and historic buildings, as they are less likely to cause damage to the underlying structure should the materials need removing. And there's some plastering membrane. The one on the left you can see has got a nylon mesh to help bonding the material on top, and you can see the little plastic blisters that hold it from the wall. It's fixed to the wall by waterproof fixings, and there's a gentleman on the right putting any old finish over it. It's completely waterproof. What about redecoration? Well, this really applies to sand cement mixes, wet mixes. Use a permeable decorative finish. Do not use vinyl or plastic finish wallpapers. These can give problems. But just as importantly, always recommend that the decoration should be regarded to be of a temporary nature for the first 12 months. Frequently people will apply an expensive decorative finish, paint or what have you, and within a few weeks, couple of weeks, it starts to be a problem because nothing has fully dried out. Do bear in mind, of course, that the above does not fully apply to dry lining systems because, in essence, they're isolated from the damp contaminated substrate. This is quite important because if you are dealing with a period or historic property, then it is highly unlikely that dense cement sand mixes will be suitable. So in order to retain the integrity of the historic background, a dry lining system is far more appropriate for the finish, and they can easily be removed without damaging the underlying historic fabric. The other important feature is beware of using lime-based materials directly on the substrate, where it is known that salt contamination and moisture is present. There is a high probability using such materials that spoiling of the finish will eventually occur. Just a couple of examples: dampness appearing on lime-based plastered wall, contaminated substrate, you can see the dampness, it's caused the spoiling. And similarly here, it was used after an injection process on a historic building. Don't use lime-based materials. Unfortunately, excellent for most uses, but not good where there is any form of dampness or salt contamination that's likely to be persistent. Rising damp above effective plasterwork. Yep, that's not that uncommon. People seem to believe that rising damp can only rise a meter, and they replaster. The replastering shuts down some of the evaporation. The damp-proof course is not fully effective, and it rises above the new plasterwork. Sometimes a result like this is simply by not replastering to a sufficient height in the first place. Some plastering defects, one on the left is cement applied over a bonding plaster. It's all fallen off. Cement is strong, shrinks on drying. Bonding plasters and gypsums expand on drying, and you get this contrary reaction and it blows off. Also, gypsum plasters are slightly soluble, and in this case you can see a bit of efflorescence on the surface where the water's passed through, gone into the cement. You may have started to get sulfate attack. The drawing on the right, problem in the north, no problem in the property for years. The occupant had a new cooker. They hacked off the old dense render that was designed to be used following a damp-proof course and buried the electrical cable in the wall. They used bonding plaster and there was a problem. Similarly here, dense cement render hacked off in places for retrofit electrical fittings. The original plasterwork was working fine, holding the moisture and salts back, but in this case they hacked it off to fit the electrical fittings. Finally, we get a floor wall junction problem, And the problem really exists around the base of the wall. You can see there the bridging of most things. It's not directly related to rising damp, but the water just bridges around there and goes up the wall and tends to cause the area of damage just above the skirting level. Dampness in buildings and diagnosis, Module 8. Sources of damp, penetrating damp. There are just a few slides here simply showing examples. Features of penetrating damp. Free water in depth in the structure. Often local to external defects. Efflorescent salts often present. No groundwater salts, although possible sodium chloride, seawater near coast due to windblown rain or spray. Eruption of finishes, plaster and paint. Localized heavy patches of mould. Mould beneath wallpaper. And windblown rain facing prevailing winds. Here we are, just a few. Missing downpipe, water pouring down the wall. Why would we worry? It's not the electricity, or rather the telephone cable. The big problem here is the penetrating water. If there's embedded timbers in there, there will be a problem, or a potential problem. Water penetration around foil-back paper, southwest facing wall, taking the prevailing winds. No foil and foil backed. You can see pinholes in the foil back paper at the bottom where water is getting through. Long-term water overflow, a lot of algae around there. It must have been flowing down there for a long period of time. There's also Pisiza fungus on that wall, although you can't see it. Severe long-term pipe leak. Again, see the water runs, and that's dry rot has developed and the fruiting body over the doorway. Rain penetration through defective mortar. Well, it was rather missing. The mortar was effectively missing between the stones. A stone-built cottage, I'm still surprised it's standing up. You've got water penetration. The chalk shows where it's once penetrated to. When I was there was no water penetration, but it poured like mad. And we got the following result. The water started to come through. No wonder the little figures look so peed off. Defective flashings on the lean-to roof. Neighbour put a lean-to roof against this utility room. Told the occupant it was condensation. Significant external defects in the finish. Look at the picture on the left closely. You can see all that render is badly cracked. Picture on the right shows looking out the front over the porch. That faced the southwest prevailing winds, and rain just poured down there through the flashing at the back. And there was no roof left, basically, or timbers in that roof, full of dry rot. Sorted growths, could use a plant or a piece of growth as a gutter stop. Mould beneath wallpaper. The mould is beneath the wallpaper, not the surface. It's caused by a water leak in this case, or rather a drain leak in both cases. And the mould is beneath the wallpaper. You can see the staining on the surface, but it is not the mould, it's only a stain. The mould is beneath the wallpaper. Water penetration from a path above. It's passing into a little room, a cellar that was converted. Note the little receptacle for the penetrating water. Water passing through plaster dabs, fixing plasterboard dry lining. Obviously the plaster dabs are very permeable. The water passes straight through. Well, no comment. I expect they use the roots as cup holders or coat hangers. And finally, how to fix a leaking gutter and overflow. Again, very ingenious, very interesting, but there we go. Note, where water penetration is identified, or indeed thought to be occurring, it is really essential to investigate any embedded timbers in these areas. Why? Failure to do so may lead to the development of rots. If it stays wet long enough, it will rot, but the timbers in such areas will always be at risk to rot. Dampness in Buildings and Diagnosis, Module 9. Atmospheric moisture and condensation. There is broadly a condensation season, and this is generally between September and April. If there is dampness outside that period, it is probably not condensation. Doesn't say it isn't, it's just probably not, less likely to be. So let's first look at temperature and relative humidity. Don't remember the figures. At 10 degrees, 7.5 grams of water vapour can be resident per kilogram of dry air. At 20 degrees, double the temperature, then 14.7 grams of water vapour can be resident per kilogram of dry air. So the warmer the air, the more water vapour it can retain. Therefore, it's very useful to know how saturated the air is with water vapour. And it's this measure of saturation that is known as the relative humidity. So, in simple terms, the amount of water vapour in the air at any given temperature, expressed as a percentage, i.e. a proportion, of the maximum amount of water vapour that can be resident at the same temperature, is known as the relative humidity. And there's a little equation, actual over maximum times 100% RH. Note that relative humidity is a proportion, as I call it. It's not an amount, it's a proportion. Well, let's imagine the air as a bucket. We'll imagine the air as a bucket. The warmer the air, the bigger the bucket. Conversely, the colder the air, the smaller the bucket. So here's our air at 20 degrees. Here's our bucket, quite big. And in our case, it's 60% full. It's 60% full. What we're going to do now is we're going to cool the air down to 15 degrees. This means our bucket is going to get smaller. But what we're now going to do is to pour the water from the left side into the 15-degree bucket. Now, as a proportion of the volume of the bucket, we have 83%. Same amount of material that was there at 20%, but because the bucket has got smaller, i.e. the air's got colder, the relative humidity has increased. Okay, let's do the same exercise. We're going to cool the air to 12 degrees. Bucket's got smaller. Pour the material to the left into this bucket. Now our bucket is 100% full. It's 100% full. Same amount of water, material, whatever you want to call it, as we've had all along, but now it's full. We're going to cool the air even further. It's gone to 10 degrees. So now what's going to happen? Well, quite simply, it becomes obvious that if we pour that material into that bucket, some of it is going to overflow. That bucket just cannot hold the amount of material that was there. And this simply, in the air, comes out of the air as condensate. And indeed, the important thing to bear in mind when we're looking at reality is that warming up the air will reduce the relative humidity. Warming up the air will reduce the relative humidity. So in a very cold environment, unheated or poorly heated, we could easily have a high relative humidity, but heat it up to a reasonable temperature for living, that relative will go down to a very reasonable level. And indeed, if we look at the difference in relative humidity, now in this case we're going to assume the same level of water vapour throughout the building. And we can see this change in relative humidity. Insulation, timber suspended floor, there's the main room, it's 44% RH at 20 degrees. The VP stands for vapour pressure, and this is a direct measure of an amount of water. It's directly related to the amount of water present. So in our hypothetical building, the air is going to move up and down, round and round, and it passes into the subfloor void, and it's cooled to 13 degrees. The relative humidity, in other words our buckets got smaller, now increases to 69%. Indeed, the water vapour goes into the roof where it's really cold, it's a very cold day out, to 9 degrees. The relative humidity in that roof space is now 96% relative humidity. Same level of water vapour all the way through. The difference is purely on temperature. So, let's look at it. You're sitting in your office or wherever, and somebody comes in and says, look, here's the drawing. I've got these two RH readings, 60% and 70%. Which is the dampest room? The answer is quite simply, you don't know. You cannot say. The temperature is unknown. It may simply be a temperature factor. You don't know. This is quite an interesting, is looking at the external atmospheric conditions, because as we'll see in later modules, the external conditions do make significant changes to the internal conditions. So what have we got here? These are relative humidities and temperatures, but note in the colder months, the relative humidities that we're getting outside between London, Manchester and Edinburgh, that's quite a long distance, are all over 80% on average. So we get very high relative humidities externally. And overall, external water vapour does significantly influence, or rather can, the internal levels. So let's have a look quickly at surface condensation. So on the right we've got a cold wall, and on the left we have an air temperature scale. And with this cold wall, this difference, we are now looking at air that is what I loosely call in the boundary layer of air against the wall. In other words, a few millimetres against the wall, where the coldness in the wall can affect the air temperature. So we'll start off a little way away from the wall, literally millimetres. We've got an air temperature of 17 degrees, and this gives us, under these conditions, a relative humidity of about 74%. But as that air slowly gets really close and starts to come into contact with the wall, it's being cold. The wall's cold. The air temperature very close to the wall is now 16 degrees. The RH is now increased to 84% thereabouts. In other words, our buckets got smaller. And the air gets closer and closer and closer to the wall until it comes into direct contact where it's cooled distinctly by the coldness in the wall, and we reach 100% relative humidity. Our bucket is full, and any more cooling, the air cannot retain the water and it overflows onto the cold surface, and this is how surface condensation occurs. The temperature at which we reach 100% relative humidity is known as the dew point temperature. The dew point temperature. Surface temperatures vary. Different materials vary in their ability to transmit heat and, of course, cold. Dense materials such as glass, steel, etc., tiles, transmit heat well, and indeed cold. Porous open materials do not conduct heat well. They make very good insulating materials because they can maintain a good temperature differential between the warm and cold sites. Coldest areas are usually on north-facing walls, possibly east-facing, and those walls, or places on those walls, are most likely to be at the highest risk to surface condensation. On west to southwest walls, dampness could be water penetration. This can sometimes occur through cavity fill. And of course, thermal bridging can occur in areas such as metal window frames, concrete lintels, doors, and other structures. So how do we visually assess surface condensation? Well, I think it's fairly obvious. Water droplets on impervious surfaces. These would include paint, glass, plastic, tiles, any impervious surface. And they're just two examples there of it occurring. And of course we can see it other droplets, very evident here. One in a hall where somebody continually smokes. It's picked up the atmospheric tar, for want of another word, and one on the right in a kitchen. We've got water droplets, and you can actually see the little water runs as they've gradually built up. Corrosion runs, if you've got exposed nail in the paint, you can see where water's run down over it and cause this staining. And the one on the right is subfloor condensate. If that continues, it could be a very, very significant problem. Interstitial condensation. Surface condensation is that which occurs on the surface. Interstitial condensation is where it occurs within the fabric of the building. The drawing there shows interstitial condensation in cavity walls, the bottom drawing. However, it can occur in solid walls, it can occur within a material anywhere basically, if the conditions are appropriate. One has to remember that water vapour moves. We'll see more of this later. Water vapour exerts a pressure. The higher the amount of water vapour in the atmosphere, the greater the vapour pressure. And it will move down its pressure gradient. And during the colder months, there's more water vapour within a property than outside, simply because of occupation. Water vapour therefore moves out through cracks and crevices, moving down its vapour pressure gradient, but it also moves through the building fabric itself. And what we have the inside here and the outside, and that's a wall. What we have is a wall temperature gradient, warmer inside than outside usually. But we can also calculate a dew point temperature gradient through the wall. And if those two cross, that is the point at which we get interstitial condensation. The condensate is forming within the fabric of the wall. Interstitial condensation is more likely to occur where there's an external vapour check which prevents the passage of moisture-laden air out through the wall, dense renders, impermeable external finishes, and where there is a high internal moisture production. Different materials will resist the movement of water vapour to a greater or lesser extent. The higher the figures, the more slowly the water vapour moves. And we can see in this figure, vapour resistivity in free air is nothing. There's no resistance, and pretty minimal in mineral fibre. The rest vary. But the important thing to bear in mind about vapour resistivity, it's additive. Each of those, if they were built on top of each other, adds, so it becomes additive and more vapour resistant. Interstitial condensation is a risk, and that risk is determined. It's calculated and not assessed physically usually. By knowing the precise structure of, let's say, the wall, the thickness and the materials and so forth, the risk of interstitial condensation can be calculated. And indeed, data on the vapour resistivity is given in a British Standard 5250 2011 and a Building Research Digest on 110. So, how is the risk calculated? Well, we put all this data and figures into equations, knowing the construction of the wall, its materials, the thickness of the materials, and we can calculate a wall temperature gradient through the wall. Similarly, by use of those calculations, we can also calculate a dew point temperature gradient through the wall, inside and outside. And if indeed those two cross, we then get interstitial condensation. Dampness in Buildings and Diagnosis, Module 10. Water vapour. Water vapour and vapour pressure. All air contains water vapour, and this exerts a pressure, vapour pressure, and that is directly related to the amount of water vapour present. The more water vapour in the air, the greater the vapour pressure. In other words, it reflects the level of water retained in the air. However, it's important to appreciate that vapour pressure is not proportional to relative humidity. Relative humidity is dependent on temperature. Vapour pressure, measured as kilopascals is not. Relative humidity and vapor pressure. There we go. On the left, relative humidity expresses the actual water vapor in the air as a proportion of the saturation level, and this can clearly be seen in the two diagrams to the left. 50% RH at 20 and 50% RH at 10. However, if we deal with vapor pressure, that reflects the actual amount of water in the air. In other words, we look at the diagram again. We're just using arbitrary units. At the 20 degrees, we have 2 units vapor pressure, and at 10 degrees, 1 unit vapor pressure. Indeed, if we increase the size of our bucket in the top diagram to 10 times the size, and put that amount of water into this much larger bucket, there will still only be 2 units of water. It's also interesting to see external atmospheric conditions, the vapor pressures. And note here, the colder months of the year, the vapor pressures are much lower than they are in the summer months. Indeed, on a cold frosty day, we could be looking at vapor pressures in the order of 4.5 to 5 kilopascals. So in the colder months, the vapor pressure externally is much lower. The lowest external vapor pressures are present during the colder months of the year. In other words, at that time the air is drier. So then, you're asked which is the dampest room. Vapor pressure on the left 1 kilopascal, vapor pressure on the right 0.9 kilopascals. Well, it's the one on the left, isn't it? Quite simply, that's got more water vapor present in the atmosphere than the one on the right. And the vapor pressure is simply reflecting the actual amount of water retained in the air. So the important factors related to surface condensation at this stage are moisture production and surface temperatures. Moisture production per day is just one of the figures. There are lots of these around and they will vary slightly, but in our case, let us make that assumption it's all spot on. 14 to 17 litres per day of water is being produced. And the other feature about water vapour in a building, it moves. Where's most water vapour produced? Get a high vapour pressure in the kitchen and bathroom, large areas of water vapour production. And because it exerts a pressure, it will move down its pressure gradient into other areas of a lower vapour pressure. And this may allow problems to occur in these areas. Also note that wind direction influences the movement of water vapour in the property. Internal and external environments, well, in an unoccupied house, there's roughly the same level of water vapour inside as out. It simply comes into equilibrium between the two. There's very little difference in vapour pressure. After all, what is a house without anybody living in it? An empty box. There's no water vapour being generated internally. However, if we look at an occupied property, during the colder months, there is more water vapour internally than outside, simply due to occupational activities. Thus, we now have a difference in vapour pressures between inside and out, and this is known as the differential or excess vapour pressure. However, during the warmer months this should not be the case, as we'll see in a later module. Ventilation is better with open windows and doors. But during the winter we do get this difference in vapour pressures, the differential vapour pressure. The total vapour pressure internally is the sum of internally generated water vapour plus the external water vapour. That gives us the total moisture vapour. So we start finishing off then with more water vapour internally than externally. It's a combination of both internally. And one can see here the relationship between internal and external vapour pressures. The bottom is the external, the red graph is the external, and as we can see that as the external levels of water vapour go up and down slowly, not the quick peaks and troughs, but overall, then so does the internal vapor pressure. It follows it. The internal levels are affected by external conditions, and sometimes this can be quite considerable. So what is the basic methodology that we could use? Well, number one, the Thermo Hygrometer. We use a Thermo Hygrometer to determine air temperature and relative humidity. Some of them will also determine the dew point. We can then use a psychometric chart to determine relative humidity dew point if we've only got the temperature and humidity. And from this we can also calculate the vapor pressure. So if we simply take temperature and humidity and look at this psychometric chart, on the right scale is relative humidity and the bottom is the temperature. Note the 100% relative humidity line where the air is fully saturated with water. It's at this stage that water will start to come out of the environment. So then, let's imagine it's 60% relative humidity at 20 degrees centigrade. We mark these on our psychometric chart, where X marks a spot where the two factors meet, and then we project a line across to the 100% mark. We cross the line to 100% and then drop a perpendicular, and this says that the dew point, i.e. the point at which condensation will occur under those conditions, is 12 degrees centigrade. Indeed, we can spread the line even further across to the left to our vapor pressure and get 1.4 roughly. So the vapor pressure under those conditions is 1.4 kilopascals and the dew point is 12 degrees centigrade. We can also use a psychometric chart to look at temperature changes to a lower relative humidity. For example, imagine it is 80% relative humidity at 15 degrees. What temperature change is required to reduce the relative humidity to 60%? Far more reasonable. Well, let's mark the spots. There's our 80% line and there's our 15 degrees. What do? We simply project the line horizontally across to the 60% RH mark or line and then drop a perpendicular. And what does that tell us? It tells us that in order to get a relative humidity under those current conditions, 80% RH at 15 degrees, to get a relative humidity of 60%, much lower, we need to increase the temperature to 20 degrees. Once we know temperatures, relative humidities and the dew point, we can look for surface temperatures by using a surface temperature thermometer. And this will tell us whether the surface is at or below the dew point or above. If it's at or below, then condensation, surface condensation should be occurring. If it's above the dew point, then it will not be. However, psychometric charts are great. What they're brilliant at doing is, when you're learning, is to have a look at the relationships between temperature and humidity and dew point. One can look at these as two-dimensional charts. However, an easier way to do it is to download one of these calculators to your computer or your telephone. Put in the temperature, put in the relative humidity, and then we get lots of other readings, including vapor pressure, as we can see halfway down in kilopascals for those particular conditions. However, the distribution of salts in plaster and condensation assessment. One cannot identify the presence of condensation by salt analysis, because condensation is an environmental event, and that's how it should be determined. So what happens sometimes? Well, there's the distribution of salts in rising damp. Basically, at the base of the wall, there is very little or very low or trace levels, often nothing of significance. A sample is removed, usually from that level, because it's easy and the damage can be covered by the skirting. It gets analysed, it shows there's free water present, no salts, therefore the client says, okay, it's clearly not rising damp, there are no salts, it must be condensation. Can't be done. If you're going to sample for anything, you go towards the top. But condensation is an environmental event and it's determined by assessing the environment. We often hear about lifestyle causing problems. So what can we regard as lifestyle? Well, for our purposes, it's water generated by occupation. A domestic property should be able to cope with all the water generated from what we could loosely call a normal lifestyle, with normally accepted activities, no overcrowding or unrealistic moisture production. So what are normal lifestyles? Well, one could argue there are extremes of normal lifestyles. For example, family 1 has cereal for breakfast and salads for tea and so forth, with minimal cooking out most of the day. Family 2 all have cooked breakfast, fully cooked dinners in the evening, with children and some occupational day. They're both extremes of normal lifestyles. The property should be able to cope with these extremes by one means or another, and appropriate systems should be in place, especially suitable ventilation. The average domestic property is not really designed to manage additional extraneous sources of water, such as unventilated dryers, etc. Just as an interesting case study, condensation is frequently the result of internal water production. It is not the result of damp walls or floors, and this I exclude flooding. But I do mention that some properties have distinctly cold areas, such as dense lintels, and that will significantly increase the risk of condensation, even though the property is regarded as having a suitably dry environment. This was a property in London, a ground floor flat, part of a much larger complex. I think there were 5 high and it was a U pattern of building. It formed a U shape. And there's the north wall, rear wall, and there was a legal case over this because the lady was losing property, had lots of mould, had real problems with her clothes and so forth, and was suing for damage. Well, the main area of visible dampness was basically the rear wall of the lounge, which was facing north. And there we go, the rear wall of the lounge facing north. And the plaintiff's expert had noticed a tide mark. And of course, everybody associates these tide marks with rising damp. And of course, the shape of it was rather odd as well. It was totally in the corner. So first thing one does is get some atmospheric data, and there it is. What it showed is the north fall surface was below the dew point, as one would expect. Indeed, the wall was actually running water. There were water literally running down the wall at the time of the inspection. And also, we were taken, the vapor pressures were measured. And the difference between internal and external, the differential vapor pressure was 1 kilopascal. That is enormous. That is enormous. But they said it was rising damp. That's where all the water was coming from, active rising damp. And their expert had noticed drill holes externally along the wall, rear wall. So anyway, we profiled the wall, and these are the results we got. Capillary, free moisture content, nothing. 0.1 is nothing. It's dry. Salts, we noticed 1200 millimeters. We had a very distinct salt band. Can happen. So the walls had rising damp, but it's no longer active. It's no longer active. Now this gave him a problem, since the walls were technically dry, was to find a source of water. There was no free water around. So where was the water coming from that was causing the plaintiff's problem? Well, this is where he went next. He claimed it was coming from a wet floor. He has no data on this. And it was coming from a wet floor and condensing on the rear wall. However, when one looks at this, it was a self-leveling floor compound with plastic tiles, and there was this tiny gap. Now, the interesting thing was there were water droplets on the plastic tiles. Why? Because that whole area of perimeter of floor was below the dew point. In other words, condensation was happening, and should have been happening because of the below dew point temperature. So what he's now saying is that water is evaporating from an area where it should be condensing and then recondensing on the wall. Well, quite simply, this is rather nonsensical. However, water evaporates from a saturated screed, remember he's talking about the floor, at room temperature at a rate of 75 grams per day for a 16 square metre floor. That's data from the Building Research Station. And in reality, a wall should be no different. An average individual's lifestyle, i.e. by occupation, can produce around up to 3,500 grams of water per day to 9,000 plus grams of water per day. Huge amounts of water compared with what could be lost from saturated screeds or walls. Thus, the origin of the water causing the severe condensation was simply the plaintiff's lifestyle, that is, her water she was producing from occupation, and it was absolutely nothing to do with dampness within the fabric of the building. However, that was a snapshot survey. And of course, the previous methodology will only give us a snapshot of the conditions at the time of the visit. But conditions change continuously, and it's likely that the conditions responsible for the problem will occur at times other than the time of the inspection or survey. It therefore frequently becomes essential in such cases to monitor the environment over a period of time in order to assess the long-term changes in conditions. Dampness in buildings and diagnosis, Module 11. Long-term assessment of atmospheric moisture and the internal environment. There's some atmospheric moisture, perfectly visible as clouds. But in the internal environment, you don't see it like that. It's simply clear, nothing effectively to be seen, except possibly the consequences of it. So how do we do long-term monitoring? Well, these are temperature and relative humidity data loggers. They'll record the temperature, relative humidity, and the dew point over a period of time. Data direct from the logger, that's with its own software. See the temperatures, dew point, and humidity. We can also convert the data to vapor pressure, and of course this is directly related to the moisture content of air. So when we compare internal moisture levels with those externally, as we found earlier, it becomes the differential or excess vapor pressure. And it's very useful because it can be used as a guide to ventilation and or moisture production by the occupants. So how do we place the data loggers? Well, very easy. Indoors, keep them away from heat sources such as radiators and lamps and fires. Keep them away from windows and try to keep them over 15 centimeters away from a wall surface. And place them where the airflow is not restricted. Also, externally, try to keep them away from direct access to elements such as rain, snow, etc. Position to allow good typical airflow. And I've always found that the simplest protection against all these is a polystyrene cup with a data logger hanging in it like a bell clap and sealing the logger in it via the piece of string. However, with a data logger, you may collect anything between sort of 500 and 2,000 bits of data. In this case, we were collecting it at half-hourly intervals. So sticking to something like a psychometric chart will take you a month of Sundays. The easiest way is to use a spreadsheet that's already set out. One simply puts the data into the spreadsheet and all the calculations are done for you. And we put in here the temperature and relative humidities. It's just an example of bedroom 1, and it automatically works out the vapor pressure and the differential vapor pressure. It's quite interesting to look at vapor pressures. This is the summer of 2010, good ventilation. Note, in the middle, there is the green line. This is what I would loosely call the neutral point. It is the balance between water inside and water outside. It's so-called neutral. And on this you can see during the warmer months of the year, on average, there's as much water in the house as there is outside. It's only as the months get colder, I'm here specifically looking at September, when we start shutting windows, that our differential vapor pressure on average starts to increase. We are now cutting down the ventilation. But with windows mostly open, during the summer months, there is no real difference between internal and external vapor pressures. But one can see that these vast variations can occur all the time, up and down, something like a yo-yo. But on average, that's the sort of result we'll get. Changing internal occupation, another job, there it is on the left. The 0 point, there's much water vapor inside as outside, and above that there's more water vapor in the building. Differential vapor pressure, occupied, unoccupied. What happened here was quite simply the first decline, around about the 15th of March, was simply they went away for a weekend. So we had no internal moisture production. They came back, we started to get pretty high internal moisture production as indicated by the differential vapor pressure. Then they went away for a long weekend, and in fact it virtually dropped again to nothing. And then when they came back it started to climb. So it does show you what is actually produced by occupancy. Another problem that arose was a kitchen with mould in the cupboards, and that's the actual data from the data loggers. And note the very high relative humidity in the cupboard where there was mould, and the very low temperature. So it was thought that there was dampness coming off the wall with the cupboard doors shut. However, when we converted those to differential vapor pressure, there's the same amount of water in the cupboard as there was in the kitchen. The mould was simply due to the colder condition and hence greater relative humidities developed within the cupboard. Looking at a database which was made up of conditions found in normal non-problem houses, and this has been used as a baseline, this suggests a differential vapor pressure of up to around about 0.45 to 0.5 kilopascals might, or rather could, be regarded as acceptable during the colder months of the year, indicating perhaps sufficient ventilation. Remember, differential vapor pressure compares the internal moisture levels with those externally. It's a measure of moisture production and or ventilation. However, if you think about it, when one is dealing with internal conditions, in many respects, it's effectively relative humidity that is the major factor. Why is this? Because it potentially leads to health problems, especially related to dust mites, mould, bacteria, viruses and so forth. That is what we refer to, in essence, a damp environment. That's what's caused these problems. Nevertheless, it's still very important to provide and look at differential vapor pressures, because they provide a guide in relation to the ventilation and or moisture production, and this is especially useful where problems are encountered. Importance of relative humidity. Well, mould can grow on some certain moisture sensitive materials by maintenance of relative humidities as low as 75 to 80%. Some require higher humidities or condensation. Given the surface temperatures of walls, especially behind cupboards, these are inevitably several degrees lower than the room temperature. In this case, the relative humidity in the boundary layer of air against such surfaces will be in excess of 5 to 20% higher than that in the room. So here we have a room at 50% RH on the left. That air comes into contact with a cold wall of 14 degrees. The air is cooled by the coldness in the wall, and the relative humidity rises to 80% in the boundary layer of air against that wall. Hence we have conditions suitable for certain moulds. Similarly, in a cold environment, that also leads to a higher relative humidity under what one could call normal airborne water levels. We saw this in the case of the cupboard earlier on. So it's important to note that in a cold environment we can raise the temperature, and this will reduce the risk of these problems as it will lower the relative humidity. Again, simple at bottom, go into a property, it's very cold, 80% relative humidity, put some heat on, drop the relative humidity to 50% if we can get the heat up to 20 degrees. We can also monitor wall surface temperatures in the long term, done by these little gizmos, or these are the ones that are easily available and they're not expensive, eye buttons. They're about the size of a penny, they look like a watch battery. Fix them to the wall, flange side down, and on the bottom diagram is the kit that is used to get the data off these. And one thing one does certainly find is that the surface temperatures follow very rapidly and relatively closely to air temperatures. However, look at the bottom diagram, and this even shows it where we're using intermittent heat. The change in surface temperature is quite rapid in relation to the air temperature. And this is shown up in a real-world example. Here we have internal surfaces and internal air temperatures. They're the top two lines. The bottom two lines are the wall surfaces. And one can see the arrows mark this. As the air temperature goes up, so does the wall surface. As the air temperature goes down, the wall surfaces go down. It's pretty rapid, this relationship between internal air temperature internal air temperature and the wall temperature. And if we look at this in another way, internal wall surfaces and external air, the influence of external temperatures is much slower and in longer term than the air temperature. Short term, internal surfaces follows the air temperature, thus in long term, internal surfaces overall slowly follow external air temperatures. And again, we can see this on these two graphs, following the wavy lines that go along. It's much slower and longer term than the internal air temperatures. Surface temperatures and dew point on furniture. It's quite an interesting one, this. We monitored the wall behind a sideboard and the back of the sideboard, the surface temperatures, did the calculations, and what we found was that the wall behind the sideboard was dropping into condensation, as we can see from the graph there, quite periodically. However, the back of the sideboard, which was simply a couple of inches away, never went into condensation. However, that was the item that had mold growth on the back of it. So there was mold growth there, no condensation. The other feature with reference to airflow, it can be improved behind objects. The air temperature influencing the surface temperature. Here was some furniture against the wall. It was very cold outside and been so for a few days. Surface temperature of the wall shown to be about 18, but the cold area where the furniture had been was only 10. This was simply because there was no airflow and we had no heat input from the air. However, take these away and the internal air temperature now influences the surface and not the coldness in the wall. So moving the furniture allows the old stagnant air flushed away and replaced with circulating warmer air. Thus, the risk of condensation and mold growth will decline. Air temperature, therefore, and associated circulation plays a very important part in warming up the surfaces of walls. This should not be underestimated. Raising surface temperatures reduces the risk of surface condensation and high relative humidities developing in the boundary layer of air. Thus, we can reduce the risk of surface condensation and mold growth on such surfaces. Even if we take a normal property per se, there are variations, especially in corners and bases of walls, in surface temperatures. And here's one example. In this case, it's the same house. In the downstairs, at one time it got up to 21 in the corner at the on the surfaces, but on the bottom it went down to 11 degrees. In essence, the wall at the base of a building can act as a thermal bridge from the cold ground. The other beauty of monitoring, it can identify intermittent problems, and in this case it was condensation during the night. So here's just an example of what was happening. Occupation on the bottom and wall surface temperatures. We've got occupation and heating at the bottom, then occupation and heating off, and occupation and heating on in the morning. And if we look at the wall surface temperatures, they go up and down according to the actual time of occupation in that particular room. If we then start monitoring atmospheric moisture, we find that goes up and down. Obviously, when they're in the room, they're going to start generating moisture. That will dissipate when they leave the room and start building up again, say, next morning. And if we look at this data roughly, or the principle of this data that was obtained, we found that condensation was occurring in the early hours of the morning before the atmospheric moisture totally dissipated, whereas the wall surface temperature was dropping quite rapidly. So this is the sort of thing that monitoring, long-term monitoring, will pick up. It can pick up, it did in this case, the problem was occurring early in the morning. Dampness in buildings and diagnosis, module 12. Mould growth. There we are, picture of mould. Note the different colours of the moulds. Not all moulds are black by any stretch of the imagination. Mould growth beneath wallpaper. The mould is beneath the wallpaper, and note it is not on the surface of the paper. These situations where mould occurs as such are caused by dampness in the substrate. Both those cases were leaks externally. You can see, however, there is on the top one some staining of the wallpaper from the mould underneath. Typical mould pattern in a corner, mould on cold spots. Effects of missing insulation and mould, little spot in the middle there, well away from the edge. Insulation was missing in part in the centre. This is nothing to do with mould. It's a phenomenon known as pattern staining, often seen on ceilings, where we've got lightweight blocks and standard mortar between. An examination showed that you're around about half a degree cooler over the mortar beds. The surface temperature is about half a degree cooler. Tape lift shows that this is simply dust. Why it collects on the colder surface, I don't know. It is simply dust. The surfaces in the cases here were well above the dew point, so it's only dust that is collecting. There are over 100,000 species of mould. Less than 100 are commonly reported in the UK, most being Penicillium and Cladosporium. Stachybotrys atra or Shatarum, a so-called toxic mould, is uncommon, but it's not rare in the UK. They have the same requirement for growth and survival as rots. Other than a source of infection, they require air, oxygen, suitable temperature, nutrients and moisture. And in the case of a mould, moisture is effectively the only controllable factor. Life cycle, same as any fungus basically. Start off at the top with a spore, lands on a suitable surface. If the conditions are right, it'll germinate, produces these very fine filaments, hyphae. They develop, and at some stage or another we will get a mycelium or fruiting body formed. Spores develop on that and they are released into the atmosphere. It's said that surface condensation is the most common cause of mould growth in the UK, but as we'll see, long-term maintenance of high humidities, that is in excess of 75% usually, without condensation, will also cause molds to develop in stagnant areas, especially on moisture-sensitive materials such as leather, cloths, paper, cardboard. We can group these molds, as we'll see in a minute, into primary, secondary and tertiary colonizing molds. What species of mold grows where depends on a number of factors, including humidity and the particular substrate. And this is the sequence of colonization of susceptible substrates. Primary colonizers, 80% RH, don't need condensation, as indeed nor do you do for secondary colonizers and tertiary colonizers. The primary and secondary colonizers can initiate and develop without surface condensation. Mold on leather goods due to high humidity. I've monitored these. Condensation never occurred. The mold on the belt is present, but there's absolutely no mold on the clothing inside. No mold on that clothing. And it's likely that a good proportion of mold growth is a result of high humidity, not directly surface condensation on clothes, beddings or backs of furniture. Indeed, to get condensation on those in the middle of a room, you're going to need steam. Common molds in buildings, there we are, another paper by Grant and Hunter, published in International Biodeterioration Bulletin. We can see there. Two of interest really are well, they're all quite of interest. You can see what the percentage is in all dwellings, and but in air samples, two of them show distinctly low levels: Fusarium and Stachybotrys. Fusarium and Stachybotrys, I believe, have very large spores. They're not very good at being airborne, and I also believe, I've been told, the Stachybotrys spores are also sticky, probably intended to be picked up by flies and so forth. Microbial contamination in buildings can vary greatly, and indeed it does this, or can do this, over extremely short periods of time. And it must also be fully appreciated that the presence of mold in a building does not constitute exposure. We now come to the toxic molds. It is not effectively a scientific description, it's a media description. But in this media description there are 4 species of mold that are considered to be a toxic mold. The most common is Stachybotrys, Stachybotrys atra. A black-brown mold. It requires cellulose substrates. It's slimy and requires wet, damp substrates such as following flooding. It is a tertiary colonizer. It needs wet stuff. Penicillium is grouped. Some Penicillium are grouped in relation to toxic molds. Aspergillus, usually Aspergillus fumigatus, which is farmer's lung. Also, Aspergillus fumigatus is present in large quantities in potting compost, greenhouses, home potting in properties, etc. And finally, Fusarium. So what are the detrimental health effects due to airborne molds? Well, there are some proven health effects, almost all from agricultural or industrial exposure: irritation of eyes, nose and throat, dermatitis, exacerbation of asthma, allergies probably the most common, and aspergillosis, that's farmer's lung. That is most common in immunosuppressed individuals. They are at most risk with reference to aspergillus or aspergillosis. Now, there are a number of reported health effects. They're not proven. Fever, flu-like symptoms, fatigue, coughing up blood, nosebleeds, dizziness, headaches, diarrhea, vomiting and liver damage. So what does the scientific press have to say about it? Well, German Mold Guide, they reported that, let's just read the thing, hypersensitivity pneumonitis, which is generally produced by repeated exposure to very high concentration of spores. In simple terms, that's 1 million to 100 million per cubic meter, which cannot be expected to occur in residential properties indoors. And there are some interesting occupational exposures. Wood mills, 1 million to 100 million per cubic metre. These are spore levels. Silos, 1 million. British farms, 1 million spores per cubic metre. Walk through a field when they're haymaking and you can easily see this with the amount of material floating around in the atmosphere. Go down, potting sheds, here we go, 7,500 spores per cubic metre of Stachybotrys shatarum. Again, very, very common in potting compost. And simply by throwing a mouldy orange in a bin, there's a paper on this, it was quite interesting, that released over 200,000 spores per cubic metre into the air. And it's very important to appreciate that in the UK there are no standards for internal spore levels in domestic environments. I'll repeat that. It's important to note that in the UK there are no standards for internal spore levels in domestic environments. So, more scientific stuff. Current evidence does not support the proposition that human health has been adversely affected by inhaled mycotoxins in the home, school or office environment. And lots of other quotes, the WHO, World Health Organization, and they simply reinforced the findings of the Institute of Medicine. That's their study group. That is, after reviewing the global and scientific and medical literature, the Institute of Medicine could not find sufficient evidence to support the argument that the normal presence of mould in residence and workplaces causes any adverse health effects. And indeed, a very similar statement from University Health Publishing and Johns Hopkins simply states, just because a particular mould can produce toxins, it doesn't mean it will. Even if the mould is producing toxins, a person must breathe in sufficient dose to be affected. It is highly unlikely that you could inhale enough mould in your home or office to receive a toxic dose. That's an atmospheric dose. And basically, they all come to the same conclusion, that there was an association between damp living conditions and some adverse health effects, but no one has ever conclusively shown it's due to mould. Most of the things are all associated with damp, and those factors are considered to be part of the etiological background. That's dust mites, bacteria, moulds, and so forth. And as such, the stress is placed on correcting the damp. So, on peer-reviewed literature, the fundamental problem is one of a long-term damp environment, and that gives rise to all kinds of other things. They are all associated with a damp environment. So whilst toxic moulds are not a total myth, they are certainly nowhere near as devastating as frequently reported in the media. And like many other factors, they're only likely to affect what I loosely call sensitive and immunosuppressed persons. By far the greatest proportion of the population will not be affected. Control of atmospheric moisture condensation and mould growth. You know all this basically, so it's just a little bit of a recap. There we are, typical ventilation rates in air exchanges per hour. Whether that's still valid, because this is from BS 5250, 2002, it's probably even lower in recent years. So what do we need to do? We need to improve the ventilation to sweep out moisture-laden air and replace with drier air from outside. How do we do that? Well, ventilation, fans, manual humidistat, controlled and constant running. The idea is to remove the water at source. This is especially important in bathrooms and kitchens. Positive pressure systems, another way of ventilating, and I refer you to Part F of the building regulation for details of ventilation rates for the different methods. Positive pressure system in the roof, it's ducted out onto the landing, and indeed another system, positive pressure in a lounge, and that's ducted out to the hall. Positive pressure systems pull in from the outside external dry air. Remember, the air outside is inevitably drier, contains less atmospheric moisture than the air inside, because the principle of ventilation is to replace damp air inside with drier air from outside. So positive pressure then is pulling in external dry air. It's creating a pressure, a small tiny pressure indoors, and that will push out the damp air. Constant running fans and bathrooms, such as in bathrooms and kitchen, are actually producing a negative pressure. They're pulling out or pushing out the damp air, and the external air is coming in via vents. Both systems require some passive ventilation to allow the intake and exhale of air. We could try, if we have a subfloor condensation problem, we could try putting polythene water, which is designed to reduce the water vapour evaporating from the oversight. But also it's essential to maintain a good airflow through enough air bricks and make sure they're clear. And very important, reduce internal atmospheric moisture. If one looks at the data that's available, in reality, one would ideally keep the relative humidity in a domestic property in the winter below an average of around 55 to 60%, assuming 20 degrees centigrade. Remember, this is an average. You're going to get the data to go up and down. And this should be the same for any property, irrespective of size and occupation. If this cannot be achieved by temperature and or ventilation, then one should investigate why. However, the primary investigation should be the ventilation, assuming reasonable temperatures, and then have a look at the heating. So, back to the control of atmospheric moisture and condensation. Improve heating, make it constant, not intermittent. Raise the temperature to bring the environment out of the mould risk area. Also bear in mind that raising the temperature will raise the surface temperature of walls and therefore reduce the risk of mould. Effects of intermittent heating on walls. This could lead to short-term intermittent surface condensation, so beware. Reduce sources of moisture. Do not use bottle gas heaters or paraffin heaters. Apparently, large dogs give off as much water vapour, if not more water vapour, than a large human. Improve surface temperatures. We could use insulation. Improve the thermal properties of wall. Keep dry. For example, if you take a solid wall and it starts to get full of water from a long rainstorm, one of the factors that affects the thermal property is the capillarity, the air in the wall, in the capillaries. If that is replaced by water, then it reduces the thermal property of the wall. So one could, if you've got that typical problem, use an external silicone. That will reduce water penetration into the wall, and it has been shown to be effective in allowing the walls to warm up. Dehumidifiers are very popular and effective. But for moulds, we need to eliminate the moisture causing the problem and clean it down. It doesn't matter what mould is present, that is the fundamental cure for all moulds. And when we're looking at moulds, it is impossible to eliminate mould and mould spores in the indoor environment. And indeed, visible mould, although not a precise measure of exposure, is probably the clearest risk indicator for potential exposure. And clean up, well, a visual and olfactory inspection is the most important step in identifying a possible contamination problem. Cleaning up is where there's no visible mould, no mouldy odours, and very important, you have fixed the moisture and water problem so that it will not recur. This is emphasised as fundamental in mould remediation. And all through the US Environmental Protection Agency documents is that it states the most practical approach is simply to eliminate all visible mold growths and smells from the environment. However, there might be some very rare cases where hidden mold may be, and I repeat, maybe or might be, a potential problem. For example, where there are known to be immunocompromised individuals. There's some really good advice from the WHO, the World Health Organization, which I think is very good. It says, I'm going to read it, management of moisture requires proper control of temperature and ventilation and so forth. Ventilation should be distributed effectively through space and stagnant air zones should be avoided. However, this, I believe, is very important. Building owners are responsible for providing a healthy workplace or living environment that is free of excess moisture and mold by ensuring proper building construction and maintenance. But what I like about this, it equally says the occupants are responsible for managing the use of water, heating and ventilation and appliances in a manner that does not lead to dampness and mold growth. I personally think that is an excellent balance of responsibility. But, and I've emphasized this, you can't emphasize it more, extremely important, if it becomes known that a sensitive individual might suffer harm from any such environmental conditions, then professional medical advice should be immediately sought by those individuals. Indeed, if anyone complains of ill health, then they should always seek medical advice from those qualified to give it. That's medically qualified. So you really need to get that advice. It is not for non-qualified people to give it. Anti-mold washes, pretty good. Bleach, suitable biocide. Anti-mold paints, they're also very useful where the problem is severe or you've got very difficult areas such as bathrooms. And that is an anti-mold paint after over 10 years of exposure compared with the non-painted equivalent. And finally, for interstitial condensation, most of the above, but especially improve ventilation, plus remove any external vapor-resistant layers that allows water vapor to pass freely out through the wall, and install internal vapor control layers on the warm side. Indeed, this is to slow the water vapor movement into the wall. Dampness in buildings and diagnosis, end of module 12. Please note, full notes of all modules may be obtained from the email address shown above.